In 1814, a young glassmaker in Munich noticed something peculiar: dark lines scattered across the spectrum of sunlight, like tiny gaps in a rainbow that no one had thought to count before. Joseph von Fraunhofer mapped hundreds of these mysterious shadows, not knowing he had handed future astronomers the key to reading starlight itself. This is a story that unfolds slowly, across more than a century, through the careful work of observers who learned to sort the stars not by their brightness or position, but by the hidden patterns in their light. From a Bavarian workshop to the quiet offices of Harvard College Observatory, where a group of women would eventually bring order to the heavens. If these gentle histories help carry you toward rest, perhaps consider subscribing, so another might find its way to you soon. The year is 1814, and we begin with glass. In the early years of the 19th century, in the Bavarian city of Munich, a young man named Joseph von Fraunhofer was engaged in the careful and painstaking work of testing optical glass, and it was during this quiet, methodical labor that he would make a discovery which, though he could not have known it at the time, would open an entirely new chapter in humanity's understanding of the stars, even though he himself would never live to see the full significance of what he had found, and even though the explanation for what he observed would remain hidden from him throughout his short and remarkable life. To understand the circumstances that brought Fraunhofer to this moment of discovery, we must first go back a little further in time, to the year 1797, when an 11-year-old boy found himself orphaned in the city of Straubing, having lost both his mother and father within the span of a few years, leaving him alone in the world with no family to support him and no obvious path forward in life. This boy was Joseph Fraunhofer, and his early years were marked by the kind of hardship that might have broken many others, as he was apprenticed to a harsh glass-cutting master named Philipp Weichselberger in Munich, where he worked long hours under difficult conditions, receiving little education and even less kindness, sleeping in a cramped workshop and learning the trade of grinding and polishing glass through sheer repetition and physical labor. Then, in the year 1801, when Fraunhofer was 15 years old, an event occurred which would change the course of his life entirely, and which some might call fortunate, though it came wrapped in what must have seemed at first like tragedy. The old building that housed his master's workshop collapsed suddenly and completely, burying young Fraunhofer beneath the rubble, and for hours he lay trapped in the darkness of the fallen structure, waiting and hoping for rescue. When the rescue finally came, it was attended by no less a figure than Maximilian IV Joseph, the Elector of Bavaria who would later become king, and who had come to the scene of the disaster to observe the recovery efforts personally. Something about the young survivor caught the Elector's attention, perhaps his resilience, perhaps simply the circumstances of his dramatic rescue, and Maximilian took an interest in the boy's welfare, providing him with a sum of money and ensuring that he would have opportunities beyond what his apprenticeship had offered. With this unexpected support, and with the additional patronage of Joseph von Utzgnade, a privy councillor who recognized the young man's talents and ambition, Fraunhofer was able to continue his education in optics while working at the Optical Institute in Benediktboien, a former monastery that had been converted into a glassworks and optical manufacturing facility. Here, in this quiet Bavarian setting, surrounded by the apparatus of precision instrument making, Fraunhofer devoted himself to the study of light and lenses with an intensity and rigor that would eventually make him one of the finest optical craftsmen in all of Europe. By 1814, Fraunhofer had risen to become one of the leading figures at the Optical Institute, and it was in this year, while conducting experiments aimed at improving the quality of optical glass for telescopes and other instruments, that he made the observation which would secure his place in the history of science. He was attempting to produce glass of exceptional purity and consistency, which required him to study the precise way that different types of glass bent and dispersed light, and for this purpose he needed a reliable and consistent source of light with known properties. The flame of a lamp, he found, was suitable for some purposes, as it produced bright yellow light that could serve as a reference point, but he also turned his attention to sunlight itself, which offered a much broader and more continuous spectrum of colors when passed through a prism. To examine the solar spectrum with the precision his work demanded, Fraunhofer constructed an arrangement involving a theodolite, which is an instrument typically used for measuring angles in surveying work, fitted with a prism and a small telescope. By allowing sunlight to enter through a narrow slit, passing it through the prism to spread it into its component colors, and then viewing the resulting spectrum through the telescope, he was able to examine the rainbow band of light with far greater clarity and magnification than had been achieved before. It was while gazing through this apparatus, expecting to see nothing more than a smooth and continuous gradation of color from red through orange, yellow, green, blue, and violet, that he noticed something unexpected, something that caught his careful eye and prompted him to look more closely. Crossing the spectrum, interrupting its smooth flow of color, were dark lines, thin and sharp and unmistakable, as if someone had drawn fine black threads across the rainbow at irregular intervals. These lines were not smudges or imperfections in his equipment, for they remained fixed in their positions no matter how he adjusted his apparatus, and they appeared consistently whenever he examined sunlight in this manner. Previous observers, including William Hyde Wollaston in 1802, had glimpsed dark features in the solar spectrum, but Wollaston had seen only a handful of such lines and had interpreted them as natural boundaries between the colors, giving them no further thought. Fraunhofer, with his superior instruments and his methodical approach, could see that these were not mere boundaries but distinct and numerous features, and he set about the task of mapping them with characteristic thoroughness. Over the months that followed, Fraunhofer catalogued the positions of these dark lines with extraordinary care, noting exactly where each one appeared in the spectrum and how strong or prominent it was. By the time he had completed his initial survey, he had identified and recorded the positions of 574 separate dark lines crossing the solar spectrum, a number that speaks to both the quality of his instruments and the patience of his observations. Among these many lines, he designated the most prominent ones with letters of the alphabet, beginning with A at the red end of the spectrum and proceeding through B, C, D, and onward to K at the violet end, and these letter designations, simple though they were, would become a standard reference system used by scientists for generations to come, with some of them still in use today when astronomers and physicists speak of spectral features. In 1817, Fraunhofer published his findings, presenting to the scientific world this detailed map of dark lines in the solar spectrum, and though he could not explain why these lines existed or what caused them to appear at their particular positions, he had documented them with such precision that other scientists could now study them as well, building upon his observations and eventually, many years later, arriving at an understanding of their true significance. He referred to them simply by his own name, calling them the dark lines of the solar spectrum, and it is a gentle irony of history that they came to be known universally as Fraunhofer lines, a term that persists in scientific literature to this day, even though Fraunhofer himself never learned what they actually were. Having completed his study of sunlight, Fraunhofer turned his attention to other sources of light, including the flames of lamps and candles, and he noticed that these artificial light sources produced their own characteristic patterns of bright lines at specific positions in the spectrum, which was itself an important observation that would later contribute to the development of spectroscopy as a scientific tool. But perhaps even more significant for the future of astronomy was his decision to turn his instruments toward the night sky, to examine not the light of the sun but the light of the distant stars themselves, a task that required both excellent telescopes and considerable patience, given how much fainter starlight is compared to sunlight. In 1823, Fraunhofer published the results of these stellar observations, reporting what he had seen when he examined the spectra of several bright stars, including Sirius, the brightest star in the night sky, and Castor, one of the twin stars of the constellation Gemini, and Betelgeuse, the red giant that marks the shoulder of Orion, and several others besides. What he found was remarkable and suggestive, for while some of the dark lines in these stellar spectra appeared at the same positions as lines in the solar spectrum, others were different, appearing at different positions or with different strengths, and the overall pattern of lines varied from star to star in ways that seemed to reflect genuine differences between the stars themselves. Here was evidence, though Fraunhofer could not have known what to make of it, that the stars were not all identical points of light but rather individual objects with their own distinct characteristics that could be read and measured through careful examination of their light. This observation, quiet and technical though it might seem, contained within it the seed of stellar spectroscopy, the science that would eventually allow astronomers to determine the temperatures, compositions, velocities, and countless other properties of stars millions of light-years away, all from the careful study of the patterns in their light. But all of this lay in the future, decades beyond what Fraunhofer would live to see. Throughout his years of observation and discovery, Fraunhofer continued his work in practical optics, designing and constructing telescopes and other instruments of unprecedented quality, and his craftsmanship was sought after throughout Europe. He developed new techniques for producing achromatic lenses, which are lenses designed to bring different colors of light to the same focus, reducing the colored fringes that had plagued earlier telescopes, and he pioneered the use of diffraction gratings, which are surfaces ruled with many closely spaced parallel lines that can spread light into a spectrum with even greater precision than a prism. His instruments were used in observatories across the continent, and his reputation as an optical craftsman was second to none. But the very work that had brought him such success was also taking a toll on his health, for the grinding and polishing of glass produced fine particles of dust that hung in the air of the workshop, and over years of breathing this dust, Fraunhofer's lungs were gradually damaged. Combined with the harsh conditions of his early apprenticeship and perhaps with a constitutional susceptibility, this occupational exposure left him increasingly weakened, and by his mid-30s it was clear that he was suffering from tuberculosis, the great wasting disease that claimed so many lives in the 19th century. Joseph von Fraunhofer died on the 6th of June, 1826, at the age of just 39 years, leaving behind a body of work that had transformed the craft of optical instrument making and that had opened a window onto the nature of light and stars, a window through which future generations of scientists would peer with ever-increasing clarity. He was buried in Munich, in the Friedhof cemetery, and on his grave was inscribed a Latin phrase that captured, with elegant simplicity, the essence of his contribution to human knowledge. The inscription reads Approximavit Sidera, which translates to He brought the stars closer, and it is difficult to imagine a more fitting epitaph for a man who had spent his life crafting the instruments and making the observations that would draw the distant universe into sharper focus. What makes Fraunhofer's story particularly poignant, in a quiet and contemplative way, is that he never knew the true significance of the dark lines he had discovered and so carefully mapped. He knew that they existed, he knew that they appeared at precise and reproducible positions in the spectrum, and he knew that different light sources, including different stars, showed different patterns of lines, but the question of what caused these lines, what physical process was responsible for their appearance, remained beyond his grasp. It would not be until the 1860s, more than 3 decades after his death, that Gustav Kirchhoff and Robert Bunsen would demonstrate that the dark lines in the solar spectrum corresponded to the absorption of light by specific chemical elements present in the outer layers of the Sun, each element absorbing light at its own characteristic wavelengths and leaving its own distinctive fingerprint in the spectrum. This understanding, when it came, transformed the Fraunhofer lines from mysterious curiosities into powerful tools for analyzing the composition of the Sun and stars, and it vindicated Fraunhofer's intuition that these lines were important and worthy of careful study, even if he could not say why. The letters he had assigned to the major lines, A through K, became standard notation for the absorption features of specific elements, with the D line, for instance, corresponding to the absorption of sodium, and the C and F lines corresponding to hydrogen, and so on through the alphabet, so that even today, when scientists speak of spectral lines, they often use Fraunhofer's original designations. And so we may think of Joseph von Fraunhofer, the orphaned apprentice who survived a building collapse and rose to become one of the great instrument makers of his age, as a man who stood at the threshold of a new understanding without quite crossing over into it, who gathered the evidence and laid the groundwork without living to see the explanation, and who left behind both a legacy of precision craftsmanship and a set of observations that would prove essential to the science of the stars. His dark lines, mysterious to him, would become the key to unlocking the composition of distant suns, and his methods of observation would be refined and extended until they formed the basis of an entirely new branch of astronomy. He brought the stars closer, as his epitaph says, not by traveling to them but by teaching us how to read the messages encoded in their light, and for this we may remember him with quiet gratitude as we drift gently towards sleep, thinking of those thin dark lines crossing the rainbow of sunlight, each one a clue waiting to be understood. And so we come now to a particularly quiet laboratory in Heidelberg, in the southwestern corner of what was then the Grand Duchy of Baden, where 2 men of rather different temperaments found themselves working side by side in the late 1850s, and where they would together make a discovery that would forever change our understanding of what stars are made of, and indeed what it means to study something that one cannot touch or visit or bring back to the workbench for closer examination. Gustav Robert Kirchhoff was a physicist, born in Königsberg in 1824, a man of careful mathematical thinking and precise theoretical frameworks, someone who preferred to work from first principles and to establish laws that could be written down and tested and relied upon, and he had come to Heidelberg University in 1854 to take up a professorship in physics, bringing with him a reputation for rigorous work on electrical circuits and on the flow of current through conductors, work that had already established certain rules that bear his name to this day in the teaching of elementary physics. Robert Wilhelm Bunsen was a chemist, 4 years older than Kirchhoff, born in Göttingen in 1811, and he had been at Heidelberg since 1852, where he had built up a laboratory devoted to the study of chemical compounds and their properties, and where he had developed, or rather perfected from earlier designs, a particular type of gas burner that would prove essential to the work they were about to undertake together, a burner that produced a flame of remarkable cleanliness and steadiness, a flame that burned so hot and so free of its own colored emissions that it could be used to heat substances and observe only the light that those substances themselves produced, without interference from the flame itself, and this instrument, which came to be known simply as the Bunsen burner, would become one of the most familiar pieces of equipment in chemistry laboratories around the world, though few who use it today may think much about the specific purpose for which its design was so carefully refined. The two men were neighbors, their homes quite close to one another, and they fell into the habit of discussing their work as colleagues and friends do, sharing observations and puzzling over problems that interested them both, and somewhere in the course of these conversations they began to focus their attention on the colored light that different chemical elements produce when they are heated in a flame, a phenomenon that had been noticed by many investigators before them, the way that sodium compounds turn a flame bright yellow, or copper salts produce a vivid green, or lithium gives off a characteristic red, and these flame colors had long been used as rough tests for identifying elements, but Kirchhoff and Bunsen wondered whether there might be something more precise hidden within that colored light, something that could be revealed if only one looked more carefully. And so they began to pass the light from their heated samples through a prism, spreading it out into its component colors, and what they saw was not a continuous smear of color but rather a pattern of bright lines, each element producing its own particular set of lines at specific positions in the spectrum, always the same lines in the same positions, as reliable and as individual as a signature or a fingerprint, and this observation, though it had been glimpsed by others before them, now became the foundation for a systematic program of investigation, a careful cataloging of which elements produced which lines, building up a reference library of spectral signatures that could be used to identify the presence of elements in any sample that could be heated and made to glow. The Bunsen burner was essential to this work because its flame was so nearly invisible, contributing almost nothing of its own to the spectrum being observed, allowing the bright emission lines of the heated element to stand out clearly against a dark background, and Bunsen and Kirchhoff refined their apparatus and their techniques, working together through 1858 and 1859, building a spectroscope that combined a prism with a small telescope for viewing the dispersed light, and gradually assembling their catalogue of elemental spectra. But it was Kirchhoff who made the crucial theoretical leap, the realization that tied their laboratory work to the mysterious dark lines that Fraunhofer had mapped in the solar spectrum 4 decades earlier, and this realization came to him through careful experimentation with the relationship between emission and absorption of light, experiments in which he passed light from a bright continuous source through a cooler gas of sodium vapor and observed that the gas absorbed light at precisely the same wavelengths where it would emit light when heated, creating dark lines in exactly the positions where bright lines would otherwise appear, and from these experiments he formulated 3 laws that describe the production of spectra under different conditions. The first of Kirchhoff's laws states that a hot solid object, or a hot dense gas, produces a continuous spectrum, a smooth rainbow of colors with no gaps or bright lines, just an unbroken gradation from red through orange and yellow and green and blue to violet, and this is the kind of spectrum one sees from the glowing filament of an incandescent lamp, or from molten metal, or from the dense hot interior of a star where the matter is packed closely enough that the light emerges as a continuum. The second law states that a hot gas at low pressure, a thin diffuse gas of atoms with space between them, produces an emission spectrum consisting of bright lines at specific wavelengths characteristic of the elements present in that gas, and this is what Kirchhoff and Bunsen were seeing in their laboratory when they heated samples of elements in the Bunsen flame and observed the resulting light through their spectroscope, each element declaring its presence through its own particular pattern of bright lines. The third law, and this was the key insight that unlocked the mystery of the Fraunhofer lines, states that a cool gas at low pressure, placed in front of a source of continuous light, produces an absorption spectrum, removing light at precisely those same characteristic wavelengths and leaving dark lines in the continuous spectrum behind it, and this absorption occurs because the atoms in the cool gas absorb photons at the wavelengths they would emit if heated, lifting electrons to higher energy states and taking that light out of the beam passing through. And with these three laws in hand, Kirchhoff understood what was happening in the Sun, where a hot dense interior produces a continuous spectrum of light, and that light must then pass through the cooler outer atmosphere of the Sun, a thinner layer of gas containing various elements, and those elements absorb light at their characteristic wavelengths as it passes through, creating the dark lines that Fraunhofer had so carefully measured and catalogued, and this meant that the Fraunhofer lines were not some property of sunlight itself but rather the signatures of elements in the solar atmosphere, each dark line corresponding to a bright emission line that could be produced in the laboratory by heating the appropriate element. The dramatic confirmation of this idea came in October of 1859, when Kirchhoff turned his spectroscope toward the Sun and examined the dark D lines that Fraunhofer had noted, the pair of dark lines in the yellow part of the spectrum, and he compared their positions with the bright yellow lines produced by sodium vapor in the laboratory, and he found that they matched exactly, the dark lines in the solar spectrum falling at precisely the wavelengths where sodium emits bright light when heated, and this could only mean one thing, that there was sodium in the atmosphere of the Sun, that the same element which gives common table salt its chemical identity, which turns a candle flame yellow when salt is sprinkled upon it, exists also in the outer layers of our star, 93 million miles away across the emptiness of space. This was a profound moment, though it unfolded quietly in the laboratory with measurements and careful comparisons rather than with dramatic proclamations, and it represented something genuinely new in the history of science, the ability to determine the chemical composition of a celestial body without traveling there, without bringing back samples, without touching or tasting or weighing the substance in question, simply by examining the light that traveled across the void to reach the observer's eye and instrument. Kirchhoff and Bunsen continued their work, and the power of their spectroscopic method was demonstrated in a particularly striking way when they discovered two entirely new elements, not by isolating them through traditional chemical separation but by noticing unfamiliar lines in the spectra of mineral samples, lines that did not match any known element in their reference catalogue. In 1860, while examining the spectrum of mineral water from Durkheim, they observed a pair of bright blue lines that belonged to no element they had yet catalogued, and they announced the discovery of a new element which they named cesium, from the Latin word cesius meaning sky blue, after the color of its most prominent spectral lines, and this was the first element in history to be discovered through spectral analysis, identified not by its weight or its reactions or its physical properties but by the unique pattern of light it emitted when heated. The following year, in 1861, they found another set of unfamiliar lines, this time dark red in color, in the spectrum of a mineral called lepidolite, and they announced yet another new element, which they named rubidium, from the Latin rubidus meaning deep red, again taking the name from the color of its characteristic spectral lines, and these two discoveries demonstrated beyond any doubt that spectroscopy was not merely a tool for identifying elements already known but a method capable of revealing elements that had never been seen before, a window into the chemical nature of matter that could show things invisible to all other methods of investigation. Meanwhile, Kirchhoff set himself to a monumental task of careful measurement and cataloguing, producing a detailed map of the solar spectrum that recorded the positions and relative intensities of thousands of dark absorption lines, far more than Fraunhofer had been able to measure with the instruments available to him, and this map, when completed and published in 1861, stretched to a length of approximately 4 meters when unrolled, a vast chart of solar absorption features. That would serve as a reference for astronomers and physicists for many years to come, a testament to the patience and precision that characterized Kirchhoff's approach to scientific work. There is a story told about this period, perhaps true and perhaps embellished in the telling, of a banker or financier who asked Kirchhoff what practical use there could possibly be in knowing the composition of the Sun, and who remarked dismissively that gold in the Sun was of no value to anyone since it could never be brought to Earth and spent, and the story continues that some time later, Kirchhoff was awarded a medal and a prize of gold sovereigns by the British government in recognition of his spectroscopic discoveries, and that upon receiving this award he sent some of the gold coins to the banker with a note observing that he had at last succeeded in extracting gold from the Sun, Though whether this exchange actually occurred or whether it has grown in the retelling as such stories often do, it captures something true about the way fundamental science sometimes appears useless to those focused on immediate practical returns, only to yield rewards that could never have been anticipated. The deeper significance of the work of Kirchhoff and Bunsen lay not in any single identification of an element or discovery of a new one, but in the philosophical shift it represented in our relationship with the cosmos, for before their work, chemistry was necessarily limited to substances that could be obtained and handled and analyzed in the laboratory, and the composition of celestial bodies seemed forever beyond the reach of human knowledge, locked away behind distances that no traveler could cross and no sample could be retrieved from. And after their work, the light itself became the messenger, carrying information about composition across any distance, and the universe changed from a collection of unreachable luminous points to a vast laboratory of matter whose chemical nature could be read in the spectra of its light. And so we come now to the work of a man whose careful observations would bring the first true order to the seemingly endless variety of stellar spectra, a priest and scientist whose quiet dedication at a rooftop observatory in Rome would lay the foundations for everything that followed. Father Angelo Secchi was born in the town of Reggio Emilia in northern Italy in the year 1818, and from an early age he demonstrated both a deep religious faith and an insatiable curiosity about the natural world, two qualities that would define his entire life and work. He entered the Society of Jesus, the Jesuit order, as a young man, and it was within this tradition of scholarship and inquiry that he would eventually find his way to the stars, carrying forward a long Jesuit heritage of astronomical research that stretched back centuries to figures like Christoph Clavius and the astronomers who had helped reform the calendar itself. The Jesuits had always maintained a particular interest in the heavens, understanding that the careful study of creation was itself a form of devotion, a way of appreciating the intricate workings of the universe. When Secchi was assigned to the Collegio Romano in Rome, he found himself at an institution with a distinguished astronomical tradition, and in 1850 he was appointed director of the observatory there, a position he would hold for nearly 3 decades until his death. The observatory itself was situated atop the church of Sant'Ignazio, and from this unlikely perch above the eternal city, Secchi would conduct observations that would change our understanding of the stars forever, working patiently night after night while the city slumbered below and the dome of St. Peter's caught the last light of the setting sun. It is worth pausing here to appreciate the rather remarkable fact that the Vatican and the broader Catholic Church actively supported and encouraged this astronomical research, providing Secchi with the instruments, facilities, and freedom he needed to pursue his investigations. Pope Pius IX took a personal interest in the observatory's work, and this papal support allowed Secchi to acquire increasingly sophisticated equipment and to dedicate himself fully to his scientific endeavors. The relationship between faith and science at the Collegio Romano was not one of tension but rather of mutual enrichment, with Secchi viewing his astronomical work as entirely consistent with his religious vocation, simply another way of exploring and celebrating the divine creation. This institutional support would prove essential for the years of patient observation that systematic stellar classification required. Secchi began his spectroscopic work in earnest around 1863, building upon the discoveries of Fraunhofer, Kirchhoff, and Bunsen that we discussed earlier. He recognized that while previous observers had examined individual stellar spectra with great care, no one had yet attempted a comprehensive survey that might reveal the underlying order in the apparent chaos of spectral diversity. The instrument that made this ambitious project possible was an objective prism attached to the Mers refractor at the Collegio Romano, a telescope of fine German craftsmanship that Secchi employed with considerable skill. An objective prism, you may recall, is positioned at the front of the telescope rather than at the eyepiece, and it spreads the light from stars into spectra before it enters the main optical system, allowing the observer to examine the spectral characteristics of celestial objects with relative efficiency. With this arrangement, Secchi embarked upon a systematic campaign of observation that would eventually encompass more than 4,000 stellar spectra, an astonishing number for the time and a testament to his patience and dedication. Night after clear Roman night, he would train his telescope upon star after star, carefully noting the appearance of each spectrum, the presence or absence of particular lines, the overall color of the continuous background, and the subtle features that distinguished one star from another. Most astronomers of the era were content to study a handful of bright stars in great detail, But Secchi understood that true classification required a broad survey, a comprehensive view that could only come from examining as many examples as possible. By 1878, he had personally classified approximately 500 stars with particular care, and these formed the core of his published catalogues and the foundation of his classification system. What Secchi discovered through this patient work was that the bewildering variety of stellar spectra was not random at all, but rather fell naturally into a small number of distinct types, each with characteristic features that appeared again and again across different stars. In 1866, he made an observation that seems obvious in hindsight but was crucial at the time, noting that the color of a star as perceived by the eye correlated strongly with the features visible in its spectrum. White and blue stars showed one pattern, yellow stars another, and red stars still another, suggesting that color and spectrum were both manifestations of some underlying physical property of the star itself. This correlation between easily observable color and the more difficult spectral analysis provided an important clue that Secchi would follow as he developed his classification scheme. His first class, which he designated Type 1, encompassed the white and bluish-white stars, objects like Sirius, the brightest star in our night sky, and Vega, that brilliant beacon of the summer heavens. When Secchi examined the spectra of these stars, he found them dominated by a series of strong, dark absorption lines that we now know are produced by hydrogen, the simplest and most abundant element in the universe. These hydrogen lines appeared broad and prominent against the blue-tinged continuous spectrum, and their strength was the defining characteristic of this stellar type. Secchi noted that stars of this class were among the most luminous in the sky, their intense white or blue-white light speaking of tremendous temperatures, though the precise relationship between spectral features and stellar temperature would not be fully understood for many years to come. The Type 1 stars presented clean, relatively simple spectra, with the hydrogen lines dominating over all other features. Type 2 in Secchi's system gathered together the yellow stars, objects more similar in color to our own Sun, and here the spectral appearance was quite different from the white stars of Type 1. Instead of a few strong, broad hydrogen lines, the spectra of these yellow stars showed a dense forest of fine, narrow absorption lines, hundreds of them crowding together across the visible spectrum. Our Sun is the prototype of this class, and when we examine its spectrum in detail, we find the signatures of iron, calcium, sodium, magnesium, and dozens of other elements, each contributing its own pattern of dark lines to the complex whole. Secchi recognized that these numerous fine lines represented a fundamentally different spectral character from the bold hydrogen features of the white stars, and he correctly grouped together stars like Capella, Arcturus, and Procyon as members of this yellow, line-rich class. The Type 2 stars seemed somehow more complex than their white cousins, their spectra dense with information that would take decades to fully interpret. Moving to cooler objects still, Secchi designated as Type 3 the orange and red stars like Betelgeuse, that ruddy shoulder of Orion, and Antares, the rival of Mars in the constellation Scorpius. The spectra of these stars presented yet another distinctive appearance, characterized not primarily by individual absorption lines but by broad bands of absorption, regions where the light was dimmed across a wide range of wavelengths rather than at specific narrow points. These band spectra, as they came to be called, arise from molecules rather than individual atoms, for in the cooler atmospheres of these red giant stars, atoms can bond together to form compounds like titanium oxide, and these molecules absorb light in broad swathes rather than at precise wavelengths. Secchi noted the distinctive pattern of these bands and the overall orange-red color of the continuous spectrum between them, correctly identifying this as a separate class of stellar objects quite different from both the white hydrogen stars and the yellow metallic line stars. His fourth type, Type 4, was reserved for an even more distinctive class of deep red stars whose spectra showed absorption bands in patterns different from those of Type 3. These were the carbon stars, objects whose atmospheres contain an unusual abundance of carbon compounds, and the bands that Secchi observed were produced by molecules like cyanogen and carbon itself. The carbon stars are relatively rare compared to the other types, and their deep ruby color sets them apart even in casual observation. Secchi correctly recognized that while these stars shared the band spectrum characteristic of his Type 3, the specific arrangement and wavelengths of the bands were sufficiently different to warrant a separate classification. The Type 4 stars would later prove to be valuable traces of stellar evolution, their peculiar compositions telling stories of nuclear processes deep within stellar interiors. In 1877, as Secchi's work neared its culmination, he added a fifth type to his system to accommodate a small number of peculiar stars whose spectra showed bright emission lines rather than the dark absorption lines that characterized all the previous types. These emission line stars, which included certain variable stars and objects we now recognize as stars surrounded by expanding shells of gas, presented a fundamentally different spectroscopic appearance, with glowing lines of hydrogen and other elements standing out brightly against the continuous spectrum. Secchi designated these as Type 5 and noted their relative rarity compared to the absorption line stars that made up the vast majority of his catalogue. The physics of emission lines, in which hot, diffuse gas glows at characteristic wavelengths rather than absorbing light from a background source, would later prove crucial for understanding not just peculiar stars but nebulae, the solar chromosphere, and many other astronomical phenomena. And so by the late 1870s, Secchi had achieved something genuinely remarkable: a comprehensive classification of stellar spectra into 5 broad types that captured the essential diversity of the stars in an organized, systematic framework. His 4 primary types, later supplemented by the 5th, demonstrated that the stellar zoo was not infinitely varied but rather fell into a manageable number of categories, each with defining characteristics that could be reliably identified with careful observation. This was exactly the kind of order that science seeks: the reduction of apparent complexity to underlying patterns, and Secchi's scheme provided a foundation upon which later astronomers could build. The influence of Secchi's work extended far beyond his own lifetime and his own observatory. When astronomers at Harvard and elsewhere began their own massive programs of stellar classification in the decades following his death in 1878, they took his basic insight, that stars could be sorted into types based on their spectral features, as their starting point. The specific details of his system would be modified, expanded, and eventually superseded by the more precise schemes developed with photographic techniques, but the fundamental approach remained the same. Secchi had shown that classification was possible, that the task of bringing order to the stars was not hopeless but rather rewarded patient, systematic observation with genuine understanding. It is fitting to remember Father Angelo Secchi not only for his scientific achievements but for the spirit in which he pursued them, combining rigorous observation with a sense of wonder and a belief that understanding the natural world was a worthy calling. From his rooftop observatory in the heart of Rome, he had surveyed thousands of stars and found in their spectra the first hints of the underlying physical principles that govern these distant suns. His work reminds us that classification, though it may seem dry and technical, is actually a profound act of understanding, a way of making sense of the universe's overwhelming complexity through careful attention and patient thought. As you drift toward sleep now, you might picture that observatory above the Roman rooftops, the dome open to the night sky, the Mers refractor pointed toward some distant star. Father Secchi at the eyepiece, the objective prism spreading starlight into its component colors, the scratch of pen on paper as he records another observation, another data point in his growing catalogue of stellar types. The city sleeps below, the dome of St. Peter's a shadow against the stars, and one dedicated observer adds another small piece to our understanding of the cosmos. His 5 types were only the beginning, a first attempt at order that would inspire all the work to come, but in science, as in so many things, it is the beginning that matters most, the first step along a path that others will continue. And now we too shall rest, as Father Secchi must have rested after long nights at the telescope, the images of stellar spectra perhaps still dancing behind his closed eyes, Type 1 and Type 2, white stars and yellow, the beautiful order hidden within the light of distant suns. In the village of Hastings-on-Hudson, situated along the eastern bank of the Hudson River some 20 miles north of New York City, there stood in the latter decades of the 19th century a private observatory that would prove instrumental in shaping the future course of stellar astronomy, though its owner could not have known the full extent of what his efforts would eventually inspire. Henry Draper was a man of considerable talent and even more considerable means, a physician by profession and an astronomer by passion, and his work in the years between 1870 and 1882 would establish the foundations upon which an entire generation of researchers would later build. The story of his contributions, and perhaps more importantly the story of what happened after his untimely death, offers a gentle illustration of how scientific progress often depends not only upon individual genius but also upon the devotion of those left behind, and upon the careful stewardship of resources dedicated to the patient continuation of unfinished work. Henry Draper was born in 1837 into a family already distinguished in American scientific circles, for his father was John William Draper, a chemist and physician who had himself made notable contributions to the emerging art of photography and who had produced, in 1840, one of the earliest successful photographic portraits. Growing up in such an environment, the younger Draper absorbed from an early age both a fascination with the physical sciences and a practical understanding of the photographic process, and these two interests would eventually combine in his hands to produce something genuinely new. He pursued medicine as his formal career, obtaining his medical degree from the University of the City of New York in 1857 and eventually rising to become a professor of physiology and later dean of the medical faculty at the same institution where his father taught. His medical practice and academic positions provided him with a comfortable income, sufficient not only for the needs of daily life but also for the pursuit of his astronomical interests on a scale that would have been impossible for a man of lesser means. It is worth noting, in that unhurried way that befits contemplation of such matters, that Draper's astronomy was never merely a casual pastime, despite the term hobby that is sometimes applied to it, for he approached his observations with the same systematic rigor that characterized his medical research, and he invested in his observatory equipment and time that would have represented a full career for many another man. The observatory that Draper constructed on the grounds of his estate at Hastings-on-Hudson was, by the standards of private observatories in that era, remarkably well equipped. Its centerpiece was a reflecting telescope with a primary mirror of 28 inches in diameter, an instrument that Draper had ground and figured himself with his own hands over many patient months of labor, for he believed that understanding the construction of his instruments was essential to using them effectively. The grinding of a telescope mirror of such size was no small undertaking, requiring the careful removal of glass in precise amounts across the entire surface, the testing and retesting of the curve, and the final polishing to a smoothness that would allow starlight to be focused without distortion. That Draper accomplished this task in his own workshop, while maintaining his medical practice and teaching duties, speaks to both his technical skill and his remarkable capacity for sustained effort. The 28-inch reflector was among the largest telescopes in America at that time, and Draper used it not merely for visual observation but increasingly for the photographic work that would become his most enduring contribution to the science. The application of photography to astronomy was still, in the 1870s, a relatively new endeavor, fraught with technical difficulties that discouraged many observers from attempting it. The photographic emulsions available at that time were slow by modern standards, requiring long exposures during which the telescope had to track the apparent motion of the stars across the sky with perfect steadiness, and the chemical processes for developing and fixing the images were not yet fully standardized. Draper, however, possessed both the technical knowledge inherited from his father's photographic work and the patience necessary to overcome these obstacles through systematic experimentation. He understood that photography offered certain advantages over visual observation, for the photographic plate could accumulate light over time, recording details too faint for the human eye to perceive, and the resulting image provided a permanent record that could be studied at leisure, measured with precision, and compared with images taken on other occasions. These advantages were particularly significant for spectroscopy, the study of starlight that has been spread into its component colors by passage through a prism or diffraction grating, because the spectra of stars are often faint and their features subtle, and the ability to examine a permanent photographic record rather than relying upon fleeting visual impressions promised a great increase in the accuracy and completeness of spectroscopic observations. On the evening of the 16th of August 1872, Henry Draper succeeded in obtaining a photograph that marked a genuine milestone in the history of stellar astronomy, though the significance of such milestones is always clearer in retrospect than it can be at the moment of their achievement. Using his telescope at Hastings-on-Hudson, he captured on a photographic plate the spectrum of Vega, the brightest star in the constellation Lyra and one of the most luminous stars visible from northern latitudes. The photograph showed not merely the continuous band of colors that one might expect from a simple source of white light, but also a series of dark lines crossing the spectrum at specific positions, lines that corresponded to the absorption of particular wavelengths of light by gases in the outer atmosphere of the star. These absorption lines, similar in nature to those that Fraunhofer had catalogued in the solar spectrum decades earlier, had been observed visually in the spectra of other stars, But Draper's photograph of the Vega spectrum represented the first time that such features had been successfully recorded by photographic means. The importance of this achievement lay not merely in the technical accomplishment itself, though that was considerable, but in the possibilities it opened for future research, for if the spectra of stars could be photographed rather than merely glimpsed, then they could be studied with far greater precision, compared systematically with one another, and eventually classified according to their characteristics in ways that visual observation alone could never have permitted. In the years following this initial success, Draper continued to refine his techniques and to extend his photographic spectroscopy to an increasing number of celestial objects. He photographed the spectra of planets, of nebulae, and of many stars across different regions of the sky, building up a body of work that demonstrated both the feasibility and the scientific value of the photographic approach. He was meticulous in his methods, keeping careful records of his observations and continually seeking to improve the quality of his photographs through adjustments to his equipment and his chemical processes. The work was slow, as all careful scientific work must be, and each clear night at the observatory brought opportunities for new observations that added incrementally to the growing collection of spectroscopic data. Draper published his results in the scientific journals of the day, contributing to the gradual accumulation of knowledge about the physical nature of the stars, and his work earned him recognition within the American scientific community as a leading figure in the application of photography to astronomical research. It was in November of 1882, at the age of just 45 years, that Henry Draper's life came to an unexpectedly early end. He had traveled to the Rocky Mountains earlier that autumn to observe a transit of Venus, one of those rare astronomical events that occurs when the planet passes directly between the Earth and the Sun, and the expedition, though scientifically productive, had been physically demanding. Upon his return home, Draper developed pleurisy, an inflammation of the membranes surrounding the lungs, and despite medical attention his condition deteriorated rapidly. He died on the 20th of November, leaving behind not only his grieving widow and his colleagues at the medical school but also an astronomical research program that was far from complete. The stellar spectra he had photographed represented only a beginning, a demonstration of what could be accomplished, and the systematic survey of the heavens that such techniques made possible remained a task for others to undertake. The loss of Henry Draper at such a relatively young age, when he might have had decades of productive work still ahead of him, was felt keenly by those who knew the value of what he had been attempting to achieve. It is at this point in the narrative that the figure of Mary Anna Palmer Draper assumes a central importance, for her response to her husband's death transformed what might have been merely a promising but incomplete research program into the foundation for one of the most ambitious astronomical projects of the 19th century. Mary Anna, who had been born into a wealthy New York family and had married Henry Draper in 1867, had shared throughout their married life in his astronomical interests, assisting him in his observations and understanding the significance of his work in ways that many spouses of scientists in that era did not. Following his death, she found herself in possession of both considerable financial resources and a deep commitment to ensuring that her husband's scientific vision would not be abandoned. The question of how best to honor his memory and continue his work occupied her thoughts in the months and years following November 1882, and her eventual answer to that question would shape the course of stellar astronomy for generations to come. In 1886, Mary Anna Draper approached Edward Pickering, the director of the Harvard College Observatory, with a proposal that was remarkable both for its generosity and for its specificity of purpose. She wished to provide funding for the continuation of the photographic spectroscopy that her husband had pioneered, supporting a systematic program of observation and analysis that would extend his work far beyond what he had been able to accomplish in his private observatory. The initial gift was substantial, but it was only the beginning of what would become a sustained commitment extending over many years, for Mary Anna Draper continued to provide financial support to the Harvard Observatory until her own death in 1914, and the total of her contributions eventually exceeded $400,000, a sum that in the currency of that era represented an enormous investment in astronomical research. This money funded not only the acquisition of equipment and the conduct of observations but also the salaries of the researchers who would analyze the resulting data, including the remarkable group of women who would come to be known as the Harvard Computers and whose contributions to stellar classification we shall consider in due course. What distinguished Mary Anna Draper's philanthropy from many other charitable gifts to scientific institutions was her personal involvement in the work she funded. She did not simply provide money and then withdraw to allow the professionals to proceed without interference, but rather maintained an active interest in the progress of the research, visiting the Harvard Observatory regularly to observe the work firsthand and to discuss the results with Pickering and his staff. Her insistence that the research program continue to reflect her husband's vision, that it remain focused on the photographic spectroscopy he had pioneered rather than drifting toward other astronomical topics, helped to maintain the coherence and direction of what became known as the Henry Draper Memorial. The catalogue of stellar spectra that eventually emerged from this work, containing classifications for hundreds of thousands of stars, bears his name to this day, a fitting tribute both to his original contributions and to the devotion of the woman who ensured that his work would not be forgotten. The broader scientific community also moved to honor Henry Draper's memory, and in 1886, the same year that Mary Anna Draper made her first gift to Harvard, the National Academy of Sciences established the Henry Draper Medal as an award for outstanding contributions to astrophysical research. This medal, which has been awarded at intervals ever since, represents an enduring recognition of Draper's role in establishing photographic spectroscopy as a fundamental tool of stellar astronomy. The first recipient of the medal, awarded in 1886, was Samuel Pierpont Langley, an American astronomer and physicist who had made significant contributions to the study of solar radiation, and the list of subsequent recipients reads as a chronicle of the most important figures in astrophysics over the past century and more. That such an honor should bear Henry Draper's name is a testament to the lasting significance of his work, even though that work was cut short before he himself could see its full flowering. In the gentle accumulation of scientific knowledge, where each generation builds upon the foundations laid by those who came before, Henry Draper's contribution remains secure, preserved both in the medal that bears his name and in the great catalogue that his widow's generosity made possible. And so we come now to the quiet work of organization, to the patient gathering of light from hundreds of thousands of distant suns, and to a man who understood that the great questions of the universe might be answered not through solitary genius alone but through the careful, methodical labor of many hands working together toward a common purpose. Edward Charles Pickering arrived at the Harvard College Observatory in 1877, and he would remain there as director for more than 4 decades, transforming what had been a modest institution into something resembling, in its own gentle way, a factory for the production of astronomical knowledge. He was not a romantic figure in the way we sometimes imagine scientists to be, not given to dramatic proclamations or sudden insights that arrived like thunderbolts from clear skies. Instead, Pickering possessed something perhaps more valuable for the work that needed doing, which was an unwavering belief in system, in method, in the accumulation of carefully verified facts that might one day, when gathered in sufficient quantity, reveal patterns too subtle for any single observer to discern. Pickering had been born in Boston in 1846, and his early career had taken him to the Massachusetts Institute of Technology, where he established one of the first physics laboratories in America designed specifically for student instruction. This experience shaped him in ways that would prove significant, for he came to believe that science ought not to be the exclusive province of a privileged few but should instead be made accessible to anyone with the patience and dedication to learn its methods. When he assumed the directorship at Harvard, he was 30 years old, and he brought with him this democratic impulse, this sense that the barriers surrounding astronomical knowledge were often artificial and could be dismantled through careful thought about how scientific work might be organized differently. The observatory that Pickering inherited was respectable but limited in scope, focused primarily on the traditional work of positional astronomy, the careful measurement of where stars appeared in the sky. But Pickering had larger ambitions, or perhaps it would be more accurate to say that he had broader ambitions, for he envisioned a survey of the heavens that would encompass not merely the positions of stars but their physical characteristics as well. The new science of spectroscopy had revealed that starlight contained information about the composition and temperature of distant suns, and Pickering understood that this information, if gathered systematically for thousands upon thousands of stars, might transform our understanding of the stellar universe. What was needed was not a handful of detailed studies of individual objects, interesting though such studies might be, but rather a comprehensive cataloging effort that would treat all stars within reach of the telescope as worthy subjects of investigation. To accomplish this vision, Pickering turned to a technique that had been developed in the preceding decades but not yet applied on a truly large scale, the objective prism photograph. The principle was elegantly simple. By placing a prism in front of a telescope's objective lens, one could spread out the light from every star in the field of view into a small spectrum, a tiny rainbow unique to that particular star. A single photographic plate might thus capture the spectra of dozens or even hundreds of stars simultaneously, each one containing in its pattern of dark absorption lines the chemical signature of a distant sun. This was enormously more efficient than the older method of pointing a spectroscope at one star at a time and studying its light in isolation, and Pickering recognized immediately that such efficiency was the key to surveying the heavens on the scale he had in mind. The observatory's initial instrument for this work was the 8-inch Bache telescope, a relatively modest refractor that had been donated to Harvard some years earlier. The telescope was fitted with an objective prism, and under Pickering's direction it began producing plates that recorded the spectra of stars across wide swaths of the northern sky. The work proceeded steadily, night after night when the weather permitted, each clear evening adding new plates to the growing archive. But Pickering understood that any survey limited to the northern hemisphere would be fundamentally incomplete, for the southern skies contained fully half the stars of the universe, including many of the brightest and most scientifically interesting objects visible from Earth. The Milky Way itself arced more splendidly through southern constellations, and the Magellanic Clouds, those mysterious patches of light visible only from southern latitudes, awaited systematic study. This recognition led to one of Pickering's most ambitious undertakings, the establishment of a southern station for the Harvard Observatory at Arequipa, in Peru. The site was chosen carefully, situated at high altitude where the atmosphere was thin and steady, and in 1891 the station became operational with its own telescope and photographic equipment. By the end of the decade, a larger instrument had joined the effort, the 24-inch Bruce photographic telescope, funded through the generosity of Catherine Wolfe Bruce, a philanthropist who supported astronomical research with remarkable dedication. The Bruce telescope was designed specifically for wide-field photography and proved extraordinarily productive, its plates capturing thousands of stellar spectra during each clear night in the dry Peruvian air. Pickering's brother, William Henry Pickering, played a significant role in establishing and operating the Arequipa station, contributing his own considerable talents to the observational work, though his career would later take somewhat different directions, including studies of the moon and planets that sparked both interest and controversy among his colleagues. The plates accumulated at a remarkable pace, arriving in Cambridge from Arequipa, stacking up alongside those produced by the Bache telescope, each one containing tiny spectral signatures waiting to be examined, measured, and classified. But here Pickering faced a problem that was as much organizational as scientific, for the sheer volume of data threatened to overwhelm any conventional approach to analysis. A single astronomer, however dedicated, could not hope to examine the spectra on hundreds of thousands of plates with the care and consistency required for reliable classification. The solution that Pickering devised was radical in its simplicity and profound in its implications. He would treat spectral classification as a form of industrial-scale data processing, applying the principles of systematic division of labor that had transformed manufacturing to the rather different enterprise of scientific research. In 1882, an opportunity arose that would provide both the funding and the institutional framework for this ambitious approach. Henry Draper had been a physician and amateur astronomer who had pioneered the photography of stellar spectra before his untimely death, and his widow, Anna Palmer Draper, wished to establish a memorial that would honor his contributions to science. Pickering proposed that the memorial take the form of a comprehensive photographic survey of stellar spectra, a project that would extend and systematize the work that Henry Draper had begun. Anna Draper agreed, and the Henry Draper Memorial became the vehicle through which Pickering's vision would be realized over the following decades. The funding she provided, which eventually totaled several $100,000, allowed Pickering to undertake the work on a scale that would otherwise have been impossible, purchasing equipment, supporting the Arequipa station, and crucially, hiring the staff needed to process the flood of photographic plates. It was in his approach to staffing that Pickering made what proved to be his most consequential decision. Rather than hiring the traditionally credentialed astronomers who would have been the obvious choice, Pickering chose instead to employ women as computers, hiring them at wages ranging from 25 to 50 cents per hour to examine the photographic plates, measure the positions and characteristics of spectral lines, and classify each spectrum according to an evolving system. The reasons for this choice were likely multiple, encompassing both the practical consideration that women's labor was significantly less expensive than men's and Pickering's genuine belief that the work required patience and attention to detail rather than advanced theoretical training. Whatever his motivations, the result was the creation of a remarkable group that would come to be known informally as Pickering's harem, though the women themselves preferred the more dignified title of the Harvard computers, and their contributions to astronomy would prove far more significant than the dismissive nickname suggested. The work these women performed was exacting and required considerable skill, despite its classification as mere computing. Each photographic plate contained dozens or hundreds of tiny spectra, each perhaps only a centimeter or two in length, and the computers examined these under magnifying glasses, noting the pattern of absorption lines, comparing them to standard reference spectra, and assigning each star to an appropriate class. The work was repetitive but demanded consistent judgment, for the boundaries between spectral classes were not always obvious, and a reliable classification system required that similar spectra receive similar classifications regardless of which computer examined them or on what day the work was done. Pickering maintained careful oversight, developing protocols and checking work for consistency, and over time the computers themselves developed considerable expertise, some of them becoming accomplished astronomers in their own right who made discoveries and theoretical contributions that extended well beyond the classification work for which they had originally been hired. Pickering also devoted considerable effort to developing instruments that would improve the quality and consistency of astronomical measurements. His meridian photometer, designed for the precise measurement of stellar brightnesses, represented a significant advance over earlier techniques and allowed the compilation of photometric catalogues that complemented the spectroscopic work. The instrument used a clever optical arrangement that allowed an observer to compare the brightness of a star directly with an artificial star of known intensity, eliminating many of the subjective errors that had plagued earlier brightness estimates. The photometric catalogues produced using this instrument became standard references, and the techniques Pickering developed influenced stellar photometry for decades afterward. Throughout his long directorship, Pickering maintained a commitment to the open publication of data that was somewhat unusual for his era, when many astronomers guarded their observations jealously as personal intellectual property. He believed that astronomical data belonged fundamentally to the scientific community, that observations made at Harvard should be freely available to any researcher who might find them useful. The observatory published extensive catalogues and made its photographic plates available for examination by visiting scientists, a policy that multiplied the scientific value of the collections far beyond what the Harvard staff alone could extract. This openness reflected Pickering's broader philosophy that the advancement of astronomical knowledge depended on cooperation rather than competition, on the patient accumulation of shared facts rather than the dramatic coups of individual genius. The scale of the enterprise that Pickering built was remarkable by any measure. Over the course of his directorship, the photographic plate collection at Harvard grew to encompass hundreds of thousands of individual images, and the spectroscopic surveys that formed the core of the Henry Draper Memorial Project eventually included the classification of more than 225,000 stellar spectra. Each of these classifications represented a small piece of information, a single data point in an enormous matrix of knowledge about the stellar universe, but taken together they formed something unprecedented, a comprehensive view of the spectral characteristics of stars across the entire sky, north and south, bright and faint, from the familiar patterns of the nearest neighbors to the dim traces of stars at the very limits of photographic detection. Pickering did not live to see the final publication of the Henry Draper catalogue, the monument to his decades of patient organization that would appear in the years following his death in 1919. But the system he had built, the methods he had developed, and the staff he had trained continued their work, bringing the great project steadily toward completion. The classification scheme that would eventually become standard, the familiar sequence of O, B, A, F, G, K, M that astronomers still use today, emerged from the work of the Harvard computers under Pickering's direction, refined and systematized through the examination of hundreds of thousands of individual spectra. It was not the achievement of a single brilliant insight but rather the product of sustained organizational effort, of treating the classification of stars as a problem to be solved through systematic labor, careful method, and the patient accumulation of carefully verified facts. And in this way, one spectrum at a time, the universe of stars began to reveal its underlying order, its patterns and regularities emerging slowly from the fog of uncollected data like a landscape gradually becoming visible through clearing mist. And so we come now to one of the most quietly remarkable stories in all of astronomical history, a story that begins not in an observatory or a university lecture hall, but in a modest household in Boston, Massachusetts, where a young Scottish woman was employed as a domestic servant, and where the circumstances of her life were about to change in ways that neither she nor anyone else could have anticipated on those ordinary mornings when she went about her ordinary duties, unaware that the stars themselves were waiting for her attention. Williamina Patten Stevens was born in Dundee, Scotland, in 1857, in a city known for its jute mills and its maritime trade, a place where working-class families lived lives of honest labor and modest expectations, and where a clever girl might hope for a decent education but would not necessarily imagine herself contributing to the great scientific questions of the age. She attended public schools in Dundee, where she showed an early aptitude for learning, and at the age of 14 she became a pupil teacher, which was a common arrangement in those days whereby bright students would assist in the instruction of younger children while continuing their own education, a system that recognized talent even when resources were limited and opportunities were few. At 20 years of age, she married James or Fleming, and the young couple made the significant decision to emigrate to America, joining the great waves of Scottish and Irish and English immigrants who crossed the Atlantic in search of better prospects and wider horizons. They settled in Boston, a city with a substantial Scottish community and a reputation for intellectual life, and for a time it must have seemed that their future was set along conventional lines. But marriages do not always unfold as expected, and James Fleming abandoned his pregnant wife not long after their arrival in the new country, leaving Williamina alone and expecting a child in a foreign land, far from her family and the familiar streets of Dundee, facing circumstances that would have defeated many people but which she met with a determination that would come to characterize her entire life. To support herself and her coming child, Williamina Fleming took a position as a housemaid in the home of Edward Charles Pickering, who was at that time the director of the Harvard College Observatory, a circumstance that might seem like mere coincidence but which would prove to be one of those small accidents of history that reshape entire fields of human knowledge. Pickering was a man of considerable scientific ambition and administrative energy, and he had undertaken a vast project to catalogue and classify the stars using the new technology of photographic plates, which could capture the spectra of hundreds of stars in a single long exposure and preserve those images permanently for study and comparison. The story of how Williamina Fleming came to join the observatory staff has been told in various ways over the years, and the precise details have become somewhat softened by the passage of time, but the general outline is that Pickering had grown frustrated with the work of one of his male assistants, finding the man's efforts at classifying stellar spectra to be careless or inefficient or otherwise unsatisfactory, and in a moment of exasperation he reportedly declared that his Scottish maid could do better work than this assistant was producing. Whether he said these exact words or something similar, and whether he meant them seriously or as mere hyperbole, the result was that in 1881, Williamina Fleming began working at the Harvard College Observatory, initially on a part-time basis and for very modest wages, but working nonetheless with the actual materials of astronomical research, the glass photographic plates that held the captured light of distant suns. The work that awaited her was at once tedious and tremendously important, requiring patience and precision and a capacity for sustained attention that not everyone possesses. The photographic plates that Pickering was accumulating showed the spectra of stars as small dark lines crossing bands of light, each pattern of lines representing the chemical signature of a distant sun, and the task was to examine these patterns carefully, to note their similarities and differences, and to sort them into meaningful categories that would allow astronomers to understand the underlying nature of stellar diversity. It was work that demanded sharp eyes and a methodical mind, and Williamina Fleming proved to have both qualities in abundance, along with something else that perhaps Pickering had not anticipated, which was a genuine intellectual engagement with the scientific questions that the work raised. By 1890, after 9 years of careful labor and increasingly sophisticated analysis, Williamina Fleming had developed a comprehensive system for classifying stellar spectra, a system that would be published as part of the Henry Draper catalog and would become known as the Draper classification system in honor of the wealthy amateur astronomer whose widow had funded much of the spectroscopic work at Harvard. The system that Fleming devised used the letters of the alphabet, from A through Q, to designate different types of stellar spectra, with the categories arranged primarily according to the strength and appearance of the hydrogen absorption lines, those dark bands in the spectrum that indicated the presence of hydrogen in a star's outer atmosphere. The letter A was assigned to stars with the strongest and most prominent hydrogen lines, and as one moved through the alphabet, the hydrogen lines became progressively weaker or were accompanied by other features that distinguished one class from another. Some letters designated stars with strong lines of other elements, some indicated stars with unusual or complex spectral patterns, and the full system encompassed the remarkable variety of stellar types that the photographic plates revealed. It was a classification scheme that imposed order on what had seemed like chaos, that gave astronomers a common vocabulary for describing and discussing the different kinds of stars, and that laid the groundwork for all the classification work that would follow. The numbers associated with Williamina Fleming's career are themselves a kind of quiet poetry, a testament to years of patient work with the spectra of the stars. Over the course of her time at the observatory, she personally classified more than 10,000 stellar spectra, examining plate after plate with her magnifying glass, noting the patterns and assigning the categories and building up a comprehensive picture of the stellar population. But classification was only part of her contribution, for her careful attention to the photographic plates led her to discover things that no one had seen before, objects and phenomena that expanded human knowledge of the universe. She identified 59 gaseous nebulae, those glowing clouds of hydrogen and other gases that mark the birthplaces and graveyards of stars, regions where the processes of cosmic creation and destruction leave their luminous traces across the sky. She discovered 310 variable stars, those fascinating objects whose brightness changes over time according to various physical mechanisms, some pulsating like great slow hearts, others eclipsed by unseen companions, others flickering through processes that astronomers were only beginning to understand. And she found 10 novae, those sudden brightenings that occur when stellar systems undergo catastrophic changes, events that had puzzled observers since ancient times and which the photographic record now allowed astronomers to study systematically. One of her most celebrated discoveries came in 1888, when she was examining a photographic plate of the region near the star Zeta Orionis in the belt of Orion, and she noticed a curious dark shape silhouetted against the glowing background of emission nebulosity, a shape that seemed to suggest the profile of a horse's head rising against the luminous gas. This was the Horsehead Nebula, which would become one of the most famous and frequently photographed objects in the entire sky, an icon of astronomical imagery that graces countless books and posters and planetarium shows, and it was first recognized by a Scottish immigrant who had come to America with nothing and had found her way to the stars through domestic service and determination and an opportunity that might so easily never have come. Perhaps even more significant for the future of astrophysics was her work in 1898, when she identified certain stars whose spectra did not fit comfortably into the existing classification categories, stars that showed peculiar features suggesting that they were fundamentally different from ordinary stars in ways that were not yet understood. Among these anomalous objects were stars that would later be recognized as white dwarfs, the dense remnants of stars that have exhausted their nuclear fuel and collapsed to extraordinary densities, objects where a mass comparable to the Sun is compressed into a volume comparable to the Earth, creating conditions utterly unlike anything in ordinary human experience. Fleming did not know what these objects were, for the physics of stellar evolution and degenerate matter was not yet developed, but she recognized that they were unusual and worthy of attention, and in doing so she took the first steps toward the identification of an entirely new class of stellar objects. In 1899, Williamina Fleming received an official appointment as curator of astronomical photographs at Harvard College Observatory, becoming the first woman to hold an official position at Harvard, a milestone that reflected both her individual achievements and the gradual, reluctant recognition that women could contribute to scientific work at the highest levels. The position acknowledged what had been true for many years, that she was responsible for managing and developing the vast archive of glass photographic plates that constituted one of the most valuable astronomical resources in the world, a collection that would eventually grow to exceed 500,000 individual plates, each one a captured moment of the sky, each one potentially containing discoveries waiting to be made by observers patient and careful enough to find them. The glass plate archive that Fleming curated was a remarkable thing, a library of light gathered over decades from observatories in both hemispheres, preserving the appearance of the sky at specific moments in time and allowing astronomers to compare observations across years and decades, to detect changes and motions and variations that would be invisible to any single night of observation. The plates were fragile and precious, sensitive to heat and humidity and handling, and their preservation and organization required constant attention and systematic care. Under Fleming's supervision, the archive became not merely a storage facility but a research resource, catalogued and cross-referenced so that astronomers could locate specific objects and specific observations with relative efficiency, a task of information management that was as important in its way as any individual discovery. Throughout all of this work, Williamina Fleming faced the persistent reality of unequal treatment and unequal pay, a reality that she noted in her own writings and that she addressed with characteristic directness. Her salary was approximately $1,500 per year at a time when male assistants with comparable responsibilities earned considerably more, and the disparity was a constant reminder that her contributions, however valued they might be scientifically, were not valued equally in the institutional structures that governed academic employment. She wrote about these frustrations in her personal journal, noting the difference between the recognition she received for her work and the compensation she received for her labor, and while she continued her work with dedication and enthusiasm, she did not pretend that the situation was fair or acceptable. In 1906, Williamina Fleming was invited to present a paper to the Royal Astronomical Society in London, an honor that placed her among the most respected astronomers of her generation and that marked a recognition of her work that transcended national boundaries. To address that august body, to present her findings on the classification of stellar spectra to an audience of professional astronomers from across Europe, was an achievement that would have seemed unimaginable to the young housemaid who had arrived in Boston alone and pregnant just a quarter-century before. The journey from domestic service to international scientific recognition was complete, and yet the journey had also just begun, for the classification system she had developed would be refined and extended by her colleagues and successors, and the archive she had built would continue to yield discoveries for generations to come. Williamina Fleming died in 1911, at the age of 54, having transformed the study of stellar spectra and having demonstrated what a person of talent and determination could accomplish even when the doors of opportunity seemed firmly closed. Her legacy lived on in the classification system she had developed, in the discoveries she had made, in the archive she had curated, and in the example she had set for other women who would follow her into the sciences. And the work of stellar classification continued at Harvard, carried forward by other women whom Pickering had hired, other computers who would refine and extend Fleming's system until the stars themselves seemed to arrange themselves in orderly ranks across the sky. And so we come now to a figure whose story unfolds with a certain quiet persistence, a woman whose observations were perhaps too perceptive for her time, and whose careful attention to detail would eventually prove essential to our understanding of the stars, though not before many years had passed and much disagreement had taken place. Antonia Caetana de Paiva Pereira Maury came to the Harvard College Observatory in 1889, and she brought with her not only an exceptional education and a family connection to the very instruments she would use, but also a particular way of seeing that would set her apart from her colleagues and, for a time, place her at odds with the director who had hired her. Her full name, with its graceful Portuguese cadences, reflected a heritage that traced back through her mother's family to distinguished lineages, but it was her American connections that would shape her astronomical career most directly. Antonia Maury was the niece of Henry Draper, that physician and amateur astronomer whose early death had set in motion the memorial project that would employ so many women at Harvard, and whose widow's generous funding made possible the very catalogue in which Maury would eventually work. Her father was a minister and naturalist, a man of broad intellectual curiosity, and her mother was Virginia Draper, Henry Draper's sister, so that astronomy and scientific inquiry formed part of the atmosphere of her childhood, as natural and present as the air she breathed. She received her education at Vassar College, which had been founded with the express purpose of providing women with educational opportunities equal to those available to men, and there she studied under Maria Mitchell, America's first professional woman astronomer and a figure of considerable renown. Mitchell had discovered a comet in 1847 and had been the first woman elected to the American Academy of Arts and Sciences, and she brought to her teaching a conviction that women could and should contribute to scientific knowledge at the highest levels. Under Mitchell's guidance, Maury developed not only technical skills in observation and calculation but also, one might suppose, a certain expectation that her work would be taken seriously on its merits, regardless of prevailing assumptions about the proper scope of women's intellectual contributions. When Maury arrived at Harvard in 1889, she joined the group of women who were then engaged in the monumental task of classifying stellar spectra for the Henry Draper Memorial. The work required patience and precision, the ability to examine photographic plates hour after hour, noting the patterns of dark lines that crossed each stellar spectrum like tiny messages waiting to be decoded. Williamina Fleming had already developed a system of classification using letters of the alphabet, and this system served well enough for the basic task of sorting stars into categories based on the presence or absence of particular spectral features. But Maury, perhaps because of her training under Mitchell, perhaps because of some quality inherent to her way of thinking, found herself noticing something more. As she examined spectrum after spectrum, she observed that the dark absorption lines did not always appear the same way, even in stars that belonged to the same general class. In some stars, the lines were sharp and narrow, crisp dark bands against the lighter background of the spectrum. In others, the lines appeared broader and somewhat hazier, as though they had been drawn with a thicker pen or had spread slightly at their edges. And in still others, the lines were diffuse and wide, lacking the precise definition of their sharper counterparts. These differences in line width and sharpness seemed to Maury to be significant, not mere variations to be overlooked in the interest of simplicity, but genuine distinctions that might tell us something important about the nature of the stars themselves. She developed a system of classification that incorporated these observations, adding Roman numeral subdivisions to indicate the character of the spectral lines. Stars with average line appearance received no special designation, but those with lines that were notably sharp and narrow she marked with the letter C, while those with hazy or diffuse lines received the letter B, and those with lines of intermediate character she designated A. It was a refinement that acknowledged what her eyes told her, that stars of apparently similar type could nonetheless differ in this subtle but consistent way, and that these differences deserved to be recorded rather than ignored. The system she published in 1897, as part of the observatory's work on the Draper Memorial Catalogue, represented hundreds of careful classifications, each one the product of attentive observation and thoughtful judgment. But Edward Pickering, the director who oversaw all the observatory's work, was not pleased with what he received. He found Maury's system too complicated, too cumbersome for the practical purposes of creating a catalogue that could be used easily by astronomers around the world. Where Fleming's system offered simplicity and efficiency, Maury's subdivisions seemed to Pickering to introduce unnecessary complexity without sufficient justification. The goal, after all, was to classify tens of thousands of stars, eventually hundreds of thousands, and a system that required such fine distinctions would slow the work considerably and might prove difficult for others to apply consistently. What followed was a period of disagreement between Maury and Pickering that must have been trying for both of them, though our records of it are necessarily incomplete, filtered through the formal language of institutional correspondence and the reticence of an era that did not encourage women to speak openly of professional disputes. Maury defended her system with conviction, arguing that the distinctions she had drawn were real and meaningful, that to ignore them was to discard information that the stars themselves were providing. Pickering maintained that practicality must take precedence, that a classification system served its purpose only if it could be applied broadly and consistently, and that Maury's refinements, whatever their merit in principle, would prove unworkable in practice. The disagreement was not merely technical but touched on deeper questions about the purpose of classification itself. Was the goal simply to sort stars into convenient categories, or was it to capture something true about their nature, even if that truth proved inconvenient to record? Maury seems to have believed the latter, and her insistence on this point put her at odds with an institutional culture that valued efficiency and output above all. Her work was published, but with reservations expressed by Pickering in his introduction, and the C designation she had worked so hard to establish was not adopted into the standard classification system that would eventually emerge. During this same period, Maury made another contribution that would prove significant, though it too received less recognition at the time than it deserved. She noticed that certain stars showed a peculiar phenomenon in their spectra, a periodic doubling of the spectral lines that would appear and then resolve, appear again and resolve again, in a regular cycle. She correctly interpreted this as evidence that these stars were not single objects at all but binary systems, pairs of stars orbiting each other so closely that they could not be separated visually but whose motion toward and away from Earth caused their spectral lines to shift and, at certain points in their orbit, to appear doubled as one star approached while the other receded. Her classification of Beta Lyrae, a star in the constellation of the Lyre, identified it as one of these spectroscopic binaries, a system whose components could be detected only through the careful analysis of light. This work contributed to a growing understanding that many stars exist not in isolation but in gravitationally bound pairs and multiples, a fact that would prove important for understanding stellar masses and, eventually, stellar evolution itself. But at the time, this contribution too was absorbed into the general work of the observatory without bringing Maury the recognition that a man in her position might have expected to receive. By the late 1890s, the combination of professional frustration and personal circumstances led Maury to leave the Harvard College Observatory. She spent years away from institutional astronomy, teaching at various schools and pursuing other interests, though she never entirely abandoned her connection to the stars. The departure must have seemed, at the time, like an ending, a talented woman whose particular gifts had failed to find their proper place in the scientific community of her day. But science has a way of circling back, of rediscovering what was once set aside, and so it was with Antonia Maury's C characteristic. In 1905 and continuing through 1907, a Danish astronomer named Ejnar Hertzsprung was engaged in work that would prove revolutionary, comparing the intrinsic brightness of stars with their spectral characteristics in ways that had not been done before. And as he pursued this work, he noticed something remarkable about the stars that Maury had designated with her C subdivision, those stars whose spectral lines were notably sharp and narrow. These C stars, Hertzsprung found, were intrinsically much more luminous than other stars of the same spectral type. They were not simply variants within their class but belonged to a distinct category altogether, stars of enormous size and luminosity that we would come to call giants. Maury's supposedly impractical refinement had, without her knowing it, identified one of the most important distinctions in stellar astronomy, the difference between the main sequence stars that make up the majority of what we see and the giant stars that represent a later stage in stellar evolution. Her careful attention to line width had captured a physical reality of profound significance, even though the theoretical framework to explain that reality would not be developed for decades yet to come. Hertzsprung wrote to Pickering, praising Maury's work and lamenting that her C characteristic had been abandoned in the standard classification system. He recognized what Pickering had failed to see, that Maury's observations contained information essential to understanding the nature of stars. It was a vindication, though one that came years after the damage to Maury's career had already been done, and though it came from across an ocean rather than from within the institution where she had worked. In time, Maury did return to Harvard, resuming her work at the observatory and continuing to contribute to stellar spectroscopy until 1935. The years of teaching had not diminished her abilities, and she took up again the patient work of examining spectra and recording what she saw. In 1933, she received the Annie Jump Cannon Prize, an award established to recognize significant contributions by women to astronomy, and it must have been gratifying to receive this recognition, named for her former colleague whose own classification system had become the standard while Maury's had been set aside. There is a certain irony in the story of Antonia Maury that settles gently over the facts like evening settling over a landscape. Her system was rejected because it was considered too complex, too impractical for the efficient work of cataloging stars, and yet the very feature that made it complex, the C designation that required noting line width as well as line presence, turned out to contain the key to one of the most important developments in stellar astrophysics. Without understanding the distinction between giant and main sequence stars, we cannot understand stellar evolution, cannot trace the life cycles of stars from birth to death, cannot make sense of the patterns we observe when we plot stellar brightness against stellar type. The information that Pickering considered dispensable was, in fact, indispensable. And so Maury's story reminds us that in science, as in so many human endeavors, what seems impractical in one moment may prove essential in the next, and that the careful observer who insists on recording what she sees, even when others tell her it is unnecessary, may be preserving exactly the data that future generations will need. She worked in an era when women's contributions to science were routinely minimized, when the path to recognition was steep and often blocked entirely, and when disagreement with a male superior could end a career. That she persisted, that she eventually returned to the work she loved, and that her observations were ultimately vindicated, speaks to a steadiness of purpose that deserves to be remembered, even if her name is less famous than those of some of her colleagues. The stars she classified still shine, of course, and the spectroscopic binaries she identified still trace their patient orbits around each other, their light shifting blue and red as they approach and recede in endless gravitational ballet. The distinction between giant and dwarf stars that her C characteristic first captured remains fundamental to our understanding of the stellar population of our galaxy. And the story of how her work was rejected and then redeemed adds one more gentle lesson to the long history of human efforts to understand the universe, a reminder that truth has its own timeline and that sometimes the most important insights arrive before we are ready to receive them. In the year 1896, a young woman of 32 years arrived at the Harvard College Observatory, stepping through the doors of a brick building that would become, in many ways, her permanent home for the next 4 decades and more. Her name was Annie Jump Cannon, and though she could not have known it then, standing at the threshold of what would become an extraordinary life's work, she would eventually classify more stars than any other human being in history, creating a system so elegant and so practical that astronomers around the world continue to use it to this very day, more than a century after she first devised it. Annie Jump Cannon was born on the 11th of December, 1863, in the town of Dover, Delaware, where her father, Wilson Cannon, served as a shipbuilder and later as a state senator. Her mother, Mary Jump Cannon, possessed a deep and abiding interest in the night sky, and it was she who first introduced young Annie to the stars, teaching her their names and positions from a small observatory constructed in the attic of their family home. Together, mother and daughter would climb up into that cramped space beneath the roof, and Mary would point out the constellations one by one, tracing their ancient patterns against the darkness while Dover slept quietly below them. These early lessons, conducted in the stillness of evening, planted seeds of curiosity that would eventually grow into something quite remarkable. As a child, Annie was known for her sharp mind and her eagerness to learn, qualities that led her parents to support her education at a time when higher learning remained largely inaccessible to women. In 1880, at the age of 16, she enrolled at Wellesley College in Massachusetts, one of the finest women's colleges in the nation, where she studied physics and astronomy under the guidance of Professor Sarah Frances Whiting. At Wellesley, she encountered her first spectroscope, a device that splits light into its component colors and reveals the hidden signatures of chemical elements, and she found herself captivated by the delicate beauty of spectral lines and the scientific information they contained. She graduated in 1884, returning home to Delaware with her degree and a deep appreciation for the methods of careful observation. Then, sometime during her early 20s, Annie contracted scarlet fever, a common but dangerous illness of the era, and though she survived, the infection left her profoundly deaf. The world of casual conversation, of overheard remarks and spoken asides, gradually fell away from her, leaving her in a quieter existence where she relied increasingly on lip reading and written communication. This loss might have discouraged a person of lesser determination, but Annie seemed to accept her deafness with characteristic steadiness, adapting to her changed circumstances and continuing to pursue her interests with undiminished energy. Some who knew her later suggested that her deafness may even have contributed to her remarkable powers of concentration, allowing her to focus on her work for hours at a stretch without distraction, though of course we cannot know this with certainty. After spending several years at home following her graduation, during which time her beloved mother passed away, Annie returned to Wellesley for postgraduate study in physics and astronomy. Her former professor, Sarah Whiting, recognized her exceptional abilities and encouraged her to seek a position at the Harvard College Observatory, where Edward Charles Pickering was then employing a team of women to analyze the photographic plates accumulating in the observatory's archives. In 1896, Annie accepted a position among these women, who were sometimes called the Harvard computers, and she began the painstaking work of examining stellar spectra that would occupy the remainder of her professional life. When Annie arrived at Harvard, she entered a project already well underway, for Williamina Fleming had been classifying stars according to her alphabetical system for more than a decade, and Antonia Maury had recently proposed her own alternative arrangement based on spectral line widths. The two systems each possessed certain merits, but they also created confusion, for astronomers attempting to use them found themselves working with incompatible classifications that did not translate easily from one scheme to another. Director Pickering assigned Annie the task of reconciling these approaches and producing a unified system that could serve as the foundation for a comprehensive catalogue of stellar spectra. Annie approached this challenge with both scientific insight and practical wisdom. She recognized that Maury's observation about the significance of temperature was fundamentally correct, and she understood that any useful classification system would need to arrange stars according to their physical properties rather than arbitrary alphabetical order. At the same time, she appreciated the simplicity and efficiency of Fleming's approach, which allowed for rapid classification during the examination of photographic plates. Drawing upon both systems, Annie developed a new arrangement that retained certain letters from Fleming's alphabet while reordering them according to stellar temperature, from the hottest blue-white stars to the coolest red ones. The sequence she established, and which remains in use today, proceeds through the letters O, B, A, F, G, K, and M, with O-type stars being the hottest and M-type stars being the coolest. Each letter class was further divided into 10 numerical subdivisions, from 0 through 9, allowing for finer distinctions within each category. Thus a star might be classified as B2 or G5 or K8, indicating not only its general spectral type but also its precise position within that type. Our own Sun, for reference, is classified as a G2 star, placing it roughly in the middle of the temperature range and within the yellow portion of the sequence. This system, which Annie first published in 1901, possessed the elegance of logical organization combined with the practicality of efficient application. The spectral types followed a natural progression based on temperature and the corresponding changes in spectral line appearance, making it possible for a trained observer to identify a star's classification quickly and reliably. Generations of astronomy students have learned to remember the sequence through a simple mnemonic phrase, "Oh be a fine girl kiss me," or in more recent variations, "Oh be a fine guy kiss me," or simply "Oh be a fine giraffe kiss me," depending on the preferences of instructor and student. These memory aids, while perhaps lacking in scientific dignity, have proven remarkably effective at helping newcomers remember the proper order of spectral types. With her system established, Annie embarked upon what would become the monumental undertaking of her career, the classification of stellar spectra for the Henry Draper catalogue. This project, funded by a memorial gift from the widow of the astronomer Henry Draper, aimed to classify the spectrum of every star visible from the northern and southern hemispheres down to a certain limiting brightness. The work required examining hundreds of thousands of photographic plates, each containing dozens or hundreds of stellar spectra, and recording the classification of each star according to Annie's system. Annie's speed at this work became legendary within the astronomical community. She developed the ability to classify stars at a rate of approximately 3 per minute, examining each spectrum, identifying its key features, and recording its classification before moving on to the next. Working at this pace for hours each day, she classified on average some 5,000 stars per month, year after year, 4 decades on end. The numbers are almost difficult to comprehend, this quiet accumulation of observations day after day in the brick building beside the observatory dome, the steady scratch of pencil on paper, the click of the plate holder, the careful rotation of the magnifying apparatus. The first volumes of the Henry Draper catalogue began appearing in 1918, and publication continued through 1924, by which time the catalogue contained classifications for some 225,300 stars. This represented more stellar classifications than had been published in all of previous astronomical history combined, and Annie had personally examined and classified nearly all of them herself. The work did not stop there, however, for she continued classifying additional stars for the Henry Draper extension, which would eventually add another 46,850 stars to the total. The extension was published posthumously in 1949, nearly a decade after Annie's death, completing a project that had occupied much of her adult life. Throughout her long career at Harvard, Annie's position remained somewhat ambiguous in terms of official recognition. Although she performed work of the highest scientific value and achieved international renown for her contributions to astronomy, she held no faculty appointment for most of her tenure, classified instead as a technical assistant despite her obvious qualifications. In 1911, 15 years after she joined the observatory staff, she was finally appointed to a permanent position, though still without the title or privileges of a faculty member. Only in 1938, when she was 74 years old and had been working at Harvard for more than 4 decades, was she finally appointed William Cranch Bond Astronomer, receiving at last the formal academic recognition that had been so long delayed. The wider world, however, proved more generous in acknowledging her achievements. In 1925, she traveled to Oxford University in England, where she became the first woman ever to receive an honorary doctorate from that ancient institution. The ceremony must have been a striking occasion, this deaf woman from Delaware standing in the medieval halls of Oxford, receiving academic honors from one of the oldest universities in the Western world, her life's work having earned her a place among the most distinguished scientists of her era. She would go on to receive numerous other honors and awards, including the Henry Draper Medal of the National Academy of Sciences and the Ellen Richards Prize, recognition that acknowledged both the quantity and the quality of her scientific contributions. Beyond her classification work, Annie made numerous individual discoveries during her examination of stellar spectra. She identified some 300 variable stars, those whose brightness changes over time according to various physical mechanisms, and she discovered 5 novae, stars that suddenly increase dramatically in brightness before fading back to their original luminosity. She also identified 1 spectroscopic binary, a pair of stars orbiting each other so closely that they cannot be distinguished visually but can be detected through periodic shifts in their spectral lines. Each of these discoveries represented a small addition to human knowledge about the universe, found in the course of her methodical examination of plate after plate. Annie Jump Cannon passed away on the 13th of April, 1941, at the age of 77, having spent 44 years at the Harvard College Observatory. In that time, she had classified more stars than any individual before or since, created a system of classification that remains the international standard more than a century later, and demonstrated through her own example that women could perform scientific work of the highest caliber. Her deafness, which might have been seen as an insurmountable obstacle, seemed instead to have sharpened her focus and deepened her patience, qualities essential to the careful work of spectral classification. The Henry Draper Catalogue and its extension remain valuable resources for astronomers today, not merely as historical documents but as practical references that continue to inform research into stellar properties and evolution. The classification system she developed has been refined and extended over the decades, with additional spectral types added for stars cooler than M-type and various luminosity classes introduced to distinguish between giants and dwarfs, but the fundamental sequence of OBAFGKM remains unchanged, a testament to the soundness of her original design. When we look up at the night sky, we are looking at stars that Annie Jump Cannon examined one by one, recording their spectral types with quiet precision in the workrooms of the Harvard Observatory. The light that reaches our eyes traveled for years or centuries or millennia before arriving here, and it carries within it the same spectral information that she decoded during those long hours of careful observation. Her work connects us to the stars in a very particular way, for she took the seemingly chaotic variety of stellar spectra and organized it into a comprehensible system, giving us a language for describing the physical nature of those distant suns. That language endures, spoken by astronomers around the world, a lasting contribution from a woman who spent her life quietly counting the stars and placing each one in its proper category, building piece by piece a census of the heavens. As the 19th century drew toward its close, and as the 20th century began to unfold with all its quiet promises of understanding, the spectral classification of stars remained, in essence, a system of careful organization without deeper explanation. The letters that Annie Jump Cannon had so methodically arranged, those familiar symbols O, B, A, F, G, K, M, represented genuine differences observed in the light of distant suns, yet the physical reasons behind these differences remained somewhat mysterious, like a beautifully organized library whose books were written in a language not yet fully deciphered. The spectra themselves were real, the patterns were consistent and reliable, but why a star of one class should display strong hydrogen lines while another showed prominent calcium, or why some stars revealed the signatures of ionized helium while others did not, these questions awaited answers that would come only through developments in fundamental physics, through patient theoretical work that would eventually connect the appearance of starlight to the actual physical conditions within stellar atmospheres. The first of these theoretical foundations was laid in the year 1900, in the city of Berlin, where Max Planck presented to the German Physical Society a remarkable solution to a problem that had troubled physicists for some years: the problem of how heated objects radiate energy across different wavelengths. Planck proposed, with characteristic caution and mathematical precision, that energy is not emitted continuously as had been assumed, but rather in discrete packets or quanta, the size of each quantum being proportional to the frequency of the radiation. This relationship, expressed through a tiny constant that now bears his name, seemed at first to be merely a mathematical convenience, a way of making the equations behave properly, yet it proved to be far more profound than even Planck himself initially recognized. The quantum hypothesis would eventually revolutionize all of physics, but for our present purposes, its importance lay in providing the first tool for understanding how temperature relates to the color and intensity distribution of light emitted by hot objects, including the glowing surfaces of stars. 13 years after Planck's foundational work, in the university town of Copenhagen, a young Danish physicist named Niels Bohr proposed a new model of the atom that would prove essential to understanding stellar spectra. Building upon Ernest Rutherford's discovery that atoms contain a small, dense, positively charged nucleus surrounded by electrons, Bohr suggested that these electrons could occupy only certain specific orbits around the nucleus, each orbit corresponding to a particular energy level. When an electron moved from one permitted orbit to another, it would absorb or emit a precise amount of energy, a quantum of light with a specific wavelength determined by the difference between the two energy levels. This elegant model explained, for the first time, why atoms produce spectral lines at particular wavelengths rather than across a continuous range, why the spectrum of hydrogen shows lines at exactly the positions observed by experimenters, why each element has its own unique pattern of lines like a fingerprint. Bohr's atomic model, published in 1913, provided the conceptual framework necessary for connecting the appearance of spectral lines to the physical conditions of temperature and density within the sources that produce them. Yet understanding why atoms produce specific spectral lines was only part of the puzzle, for the lines observed in stellar spectra depend not only on which atoms are present but also on the physical state of those atoms, whether they are neutral or ionized, whether they are in their ground state or excited to higher energy levels. A star might contain abundant hydrogen and yet show weak hydrogen lines if conditions are not favorable for hydrogen atoms to absorb light at those particular wavelengths, while another star with less hydrogen but different temperature and pressure might display hydrogen lines of striking prominence. The connection between spectral appearance and stellar composition was thus far more subtle than a simple correspondence, and unraveling this complexity required a theoretical treatment of how temperature and pressure together determine which atoms are ionized and which energy levels are populated. This crucial theoretical advance came in 1920 from Meghnad Sohar, a young physicist working in Calcutta, who applied the principles of thermodynamics and statistical mechanics to the problem of atomic ionization in stellar atmospheres. Sohar's ionization equation, as it came to be known, provided a mathematical relationship showing how the degree of ionization of any element depends upon temperature and pressure, allowing astronomers to predict, for a given set of physical conditions, what fraction of atoms would be neutral, what fraction would have lost one electron, what fraction would have lost two, and so forth. Combined with the understanding of atomic energy levels that had emerged from Bohr's work and subsequent developments in quantum theory, Sohar's equation meant that the strength of any spectral line could now be related, at least in principle, to the temperature and pressure of the stellar atmosphere producing it. The implications were profound and far-reaching, for it became possible to move beyond mere classification toward genuine physical understanding, to determine actual temperatures and pressures from the observed spectra rather than simply assigning stars to categories based on appearance alone. At Cambridge University in England, the theoretical physicist Ralph Fowler and his younger colleague Edward Milne took up the task of applying these new physical insights to the detailed analysis of stellar atmospheres. In 1923, Fowler and Milne published influential work developing the theory of spectral line formation in stellar atmospheres, showing how the principles of atomic physics and thermodynamics could be combined to predict the appearance of stellar spectra under various conditions of temperature and pressure. Their analysis provided a quantitative framework for understanding why the spectral sequence from O through M corresponded to a sequence in temperature, with the hottest stars showing ionized helium lines because only at extremely high temperatures would helium atoms lose electrons, while cooler stars displayed neutral atoms and even molecules that could survive only when temperatures were sufficiently low. Milne in particular continued to develop the theory of stellar atmospheres throughout the 1920s, establishing methods that would be refined and extended by subsequent generations of astrophysicists. It was within this context of rapid theoretical development that a young graduate student named Cecilia Payne arrived at Harvard College Observatory in 1923, coming from Cambridge where she had studied under Fowler and absorbed the new physics of atoms and quanta. Payne recognized that the theoretical tools now existed to address a fundamental question, the actual chemical composition of stars, and she set about applying Sohar's ionization equation and the methods of stellar atmosphere theory to the extensive collection of spectra that Harvard had accumulated over decades. Her approach was systematic and thorough, analyzing the strengths of spectral lines from many different elements across stars of various spectral types, using the new physics to account for how temperature affected line strength, and thereby attempting to determine the actual abundances of elements in stellar atmospheres rather than merely cataloging spectral features. The results of Payne's analysis, presented in her doctoral thesis of 1925, were startling and initially difficult to accept. Her careful application of ionization theory to the observed spectra led to the conclusion that stars are composed primarily of hydrogen and helium, with all other elements present in far smaller quantities. The abundance of hydrogen in particular appeared to be enormous compared to heavier elements, a finding that seemed to contradict the prevailing assumption that stars had roughly the same composition as the Earth, with iron, silicon, oxygen, and other familiar elements making up the bulk of their material. This assumption, though never rigorously tested, had seemed reasonable to many astronomers, and Payne's conclusion that hydrogen-dominated stellar composition was met with considerable skepticism. Henry Norris Russell, by then one of the most influential figures in American astronomy, reviewed Payne's thesis and advised her to treat the hydrogen and helium abundances as probably spurious, likely the result of some unknown factor not accounted for in the analysis. Russell was not hostile to Payne or to her work, which he recognized as exceptionally capable, but the conclusion seemed too extreme, too much at odds with expectations, and he suggested that she present this particular finding as uncertain rather than definitive. Payne complied with this advice, and her thesis, while recognized as brilliant and groundbreaking in its methods, did not immediately establish the hydrogen-rich composition of stars as accepted fact. The thesis was later described by the astronomer Otto Struve as undoubtedly the most brilliant doctoral thesis ever written in astronomy, high praise that acknowledged both its methodological sophistication and the fundamental importance of its conclusions, even though those conclusions required several more years to gain full acceptance. The vindication of Payne's findings came gradually as additional evidence accumulated and as theoretical understanding deepened. Russell himself, conducting his own analysis of spectral data using methods that had continued to develop since Payne's work, came to recognize that her conclusions had been correct all along. In 1929, Russell published a substantial paper on the composition of the Sun in which he confirmed the overwhelming abundance of hydrogen, generously acknowledging Payne's priority in reaching this conclusion through her earlier thesis work. The recognition of hydrogen as the dominant constituent of stars, and of the universe more broadly, was now firmly established, though it had taken 4 years for the scientific community to fully accept what Payne had demonstrated. With the acceptance of these theoretical advances, the temperature sequence of stellar spectral classes became clearly understood. The Class O stars, those showing lines of ionized helium and highly ionized heavier elements, were revealed to be the hottest, with surface temperatures reaching 30,000 Kelvin or more, hot enough to strip electrons from helium atoms and ionize most other elements multiple times. The Class B stars, somewhat cooler at around 10,000 to 30,000 Kelvin, showed neutral helium lines along with hydrogen. Class A stars, with temperatures near 10,000 Kelvin, displayed the strongest hydrogen lines because conditions were optimal for hydrogen atoms to absorb light at the Balmer wavelengths without being too ionized to do so. Progressing through the classes F, G, and K, with temperatures declining from around 7,000 down to 4,000 Kelvin, the spectra showed increasing prominence of lines from neutral metals and singly ionized calcium. Finally, the Class M stars, coolest of the main types at around 3,000 Kelvin, displayed not only atomic lines but also molecular bands, signatures of compounds like titanium oxide that could form only in the relatively cool conditions of these stellar atmospheres. The transformation that had occurred over these 3 decades, from 1895 to 1925, was profound in its implications for the nature of astronomical knowledge. What had begun as a descriptive taxonomy, a system of letters assigned to categories of spectral appearance much as a naturalist might classify birds by plumage, had become a quantitative physical science in which the same letters now represented measured temperatures, understood ionization states, and determined abundances. The sequence OBAFGKM was no longer merely a mnemonic for memorizing an arbitrary order but a genuine physical progression from hottest to coolest, from most ionized to least, with each class corresponding to a definite range of surface temperatures and atmospheric conditions. Classification had been transformed from stamp collecting, as some physicists were wont to dismiss descriptive science, into genuine astrophysics, the application of physical principles to understand celestial objects. The work of Planck and Bow, of Sohar and Fowler and Milne, of Payne and Russell, had together achieved something remarkable, the extension of laboratory physics to the distant stars. The same quantum principles that explained the spectrum of a discharge tube in a physics laboratory now explained the spectra of suns located at distances of many light years. The same thermodynamic relationships that governed the behavior of gases on Earth applied equally to the tenuous outer layers of stellar atmospheres. The universe, it had been shown, operates according to the same physical laws throughout, and the light from distant stars carries within it detailed information about the temperatures, pressures, and compositions of its sources, information that patient observation and careful theory could decode. As you rest now and let these thoughts settle gently, you might find comfort in this cosmic unity, this knowledge that the same atoms, the same physics, the same fundamental principles connect the matter of your own body to the matter of stars beyond counting, all governed by the quiet regularities that these scientists worked so diligently to understand. And so we come now to a rather remarkable chapter in our story, one in which the careful work of spectral classification found itself transformed into something far more profound, a tool not merely for sorting stars by their light, but for understanding the very lives that stars lead across the vast stretches of cosmic time. This transformation came about through the independent efforts of two astronomers working on opposite sides of the Atlantic Ocean, each arriving at similar insights through their own careful observations, and each contributing essential pieces to what would become one of the most important diagrams in all of modern science. The period from roughly 1905 to 1914 would see the birth of what we now call the Hertzsprung-Russell diagram, and in tracing its development, we find a gentle story of patient observation, quiet correspondence, and the gradual recognition that the Harvard classification system, that careful alphabetical ordering of stellar spectra, held within it secrets about stellar nature that its creators had not fully anticipated. We begin in Copenhagen, in the early years of the 20th century, where a Danish astronomer named Ejnar Hertzsprung was pursuing his studies of the stars with a methodical curiosity that would prove extraordinarily fruitful. Hertzsprung had come to astronomy through an unusual path, having trained originally as a chemical engineer and having worked for some years in that profession before turning his attention fully to the heavens. Perhaps this background in practical chemistry gave him a particular appreciation for careful measurement and systematic classification, for his approach to stellar astronomy was marked by a patient attention to detail that would serve him well. Between 1905 and 1907, Hertzsprung undertook a careful study of the relationship between the colors of stars, their spectral classifications according to the Harvard system, and their intrinsic brightnesses, which is to say, how luminous they truly were rather than merely how bright they appeared from our earthly vantage point. What Hertzsprung noticed, through his careful examination of the available data, was something that had not been fully appreciated before, namely that stars belonging to the same spectral class, stars showing essentially identical patterns of absorption lines in their spectra and therefore presumably having similar surface temperatures, could nevertheless differ enormously in their true luminosities. Consider, for instance, two stars both classified as type K in the Harvard system, both showing the characteristic spectral features of moderately cool stellar surfaces, both glowing with that warm orange-red light that such temperatures produce. One might reasonably expect such stars to be fundamentally similar objects, yet Hertzsprung found that some K-type stars were intrinsically quite faint, comparable in luminosity to our own sun or even somewhat dimmer, while others were enormously luminous, pouring forth light at rates hundreds or thousands of times greater than the sun despite having similar surface temperatures. This observation led Hertzsprung to propose a distinction that would prove fundamental to our understanding of stellar nature, the distinction between what he termed giant stars and dwarf stars. The giant stars, Hertzsprung reasoned, must be physically enormous objects, for if they had surface temperatures similar to the dwarf stars of the same spectral class, yet were far more luminous, the only explanation was that they possessed vastly greater surface areas from which to radiate their light. A star glowing at a particular temperature emits a certain amount of light per unit of surface area, and so a star that is, say, 100 times more luminous than another star of the same temperature must have 100 times the surface area, which is to say, it must be roughly 10 times larger in diameter. Hertzsprung published his findings in 1905 and again in 1907, writing in German in a photographic journal that was perhaps not widely read by the broader astronomical community, and so his important insights did not immediately receive the attention they deserved. Nevertheless, the essential observation had been made, the recognition that spectral class alone did not tell the whole story of a star's nature, that within each temperature class there existed stars of dramatically different sizes and luminosities. Across the Atlantic Ocean, at Princeton University in New Jersey, another astronomer was independently pursuing similar questions, though he would arrive at his insights through a somewhat different approach. Henry Norris Russell was a thoroughly American astronomer, trained in the Princeton tradition and deeply engaged with the theoretical questions of stellar astronomy. Between roughly 1910 and 1913, Russell undertook a systematic study of the stars for which reliable distance measurements were available, allowing him to calculate their absolute magnitudes, which is to say, their intrinsic luminosities expressed in the astronomical magnitude system. Russell's approach was to plot these absolute magnitudes against the spectral types assigned by the Harvard classification, creating a diagram in which each star could be represented as a single point, its horizontal position determined by its spectral class and its vertical position determined by its true brightness. When Russell constructed such plots, using data for the stars whose distances had been determined through parallax measurements and other techniques, a striking pattern emerged. The stars did not scatter randomly across the diagram, as one might have expected if spectral type and luminosity were unrelated properties. Instead, they clustered along particular regions of the plot, forming distinct groupings that suggested some underlying physical relationship between a star's temperature and its brightness. The most prominent feature was a diagonal band running from the upper left of the diagram, where the hot blue-white stars of spectral classes O and B resided with their high luminosities, down toward the lower right, where the cool red stars of class M clustered with their modest light output. This band, which Russell and others would come to call the main sequence, contained the majority of the stars in Russell's sample, and it suggested that for most stars, there existed a definite relationship between surface temperature and intrinsic brightness, hotter stars being more luminous and cooler stars being fainter, in a systematic way. Yet Russell also noticed, as Hertzsprung had before him, that not all stars fell upon this main sequence band. Some stars, particularly those of cooler spectral types, appeared well above the main sequence, possessing luminosities far greater than the main sequence stars of similar temperature. These were the giant stars that Hertzsprung had identified, and their presence in the diagram as a distinct population, separated from the main sequence by a significant gap, confirmed and extended the Danish astronomers' earlier findings. Russell's plots made visible, in a single elegant diagram, the fundamental distinction between the common dwarf stars of the main sequence and the rare but spectacular giant stars that towered above them in luminosity. The year 1913 proved to be a particularly significant one in the development of these ideas, for it was in that year that Hertzsprung and Russell first met in person and came to appreciate the complementary nature of their work. The occasion was an astronomical conference held in Bonn, Germany, where astronomers from across Europe and America gathered to discuss the latest developments in their field. Hertzsprung and Russell found themselves in conversation, comparing notes on their independent studies, and recognizing that they had each, through their own methods and observations, arrived at essentially the same fundamental insight about the nature of stellar populations. This meeting in Bonn marked the beginning of a mutual recognition and respect between the two astronomers, and it helped to establish the diagram that bore both their names as a cornerstone of stellar astronomy. In June of 1913, Russell presented his findings to the Royal Astronomical Society in London, sharing with that distinguished body his diagrams showing the distribution of stars according to spectral type and absolute magnitude. The presentation made a considerable impression on the assembled astronomers, for the patterns that Russell had discovered seemed to offer a new window into the physical nature of the stars. Here was a simple graphical representation that revealed, at a glance, the existence of distinct stellar populations and suggested that the life histories of stars might be read from their positions within the diagram. Russell followed this presentation with an article published in the journal Nature in December of that same year, bringing his findings to a still wider audience and cementing the importance of the diagram that would soon bear his name alongside that of Hertzsprung. Let us consider, for a moment, some specific examples of stars and their places within this revolutionary diagram, for such examples help to make concrete the abstract patterns we have been describing. The star Betelgeuse, that ruddy beacon marking the shoulder of Orion in our winter skies, appears in the upper right region of the Hertzsprung-Russell diagram, its cool red color placing it among the M-type stars on the horizontal axis, while its tremendous luminosity, some 100,000 times that of our Sun, elevates it far above the main sequence on the vertical axis. Betelgeuse is thus revealed as a red giant of truly enormous proportions, a star so vast that if placed at the center of our solar system, its surface would extend beyond the orbit of Mars. Our own Sun, by contrast, appears as a modest yellow point along the main sequence, its spectral classification of G2 placing it among the yellow-white stars of intermediate temperature, while its luminosity, which serves as our standard unit for measuring stellar brightness, positions it squarely within the band of ordinary dwarf stars that make up the main sequence. In the modern notation, we describe the Sun as a G2V star, where the Roman numeral 5 indicates its main sequence or dwarf status, distinguishing it from the giants that share its spectral class. And then there is the curious case of Sirius B, the faint companion to the brilliant star Sirius that had puzzled astronomers for decades before the Hertzsprung-Russell diagram provided a framework for understanding its peculiar nature. Sirius B, when finally studied spectroscopically and placed upon the diagram, appeared in a most unexpected location, showing the hot blue-white spectrum of an A-type star, which should have indicated high luminosity, yet possessing an actual brightness far below that of the main sequence, fainter even than our own cooler Sunday. This anomalous position, in the lower left corner of the diagram where hot temperatures combined with low luminosity, indicated that Sirius B must be an extraordinarily small and dense object, a star with the surface temperature of a main sequence, a star compressed into a volume no larger than that of the Earth. Such objects would come to be called white dwarfs, and their presence in the Hertzsprung-Russell diagram, occupying a region quite separate from both the main sequence and the red giant branch, demonstrated that the diagram was capable of revealing stellar populations that had not been previously recognized or understood. The power of the Hertzsprung-Russell diagram lay not merely in its ability to display the current properties of stars, but in its suggestion that the positions of stars within the diagram might change over the course of their lives, that the diagram might serve as a kind of map through which stars moved as they aged and evolved. This evolutionary interpretation of the diagram would be developed more fully in subsequent decades, as astronomers came to understand the nuclear processes that power the stars and that drive their gradual changes over time. A star like our Sun, we now understand, spends the majority of its active life on the main sequence, steadily converting hydrogen to helium in its core, before eventually exhausting this fuel supply and swelling into a red giant that occupies the upper right region of the diagram, and finally contracting into a white dwarf that settles into the lower left corner. The Hertzsprung-Russell diagram thus became not merely a classification tool but a framework for understanding stellar evolution, a map of stellar life histories upon which the entire subsequent development of astrophysics would be built. In this way, the Harvard classification system, that careful ordering of stellar spectra developed by Williamina Fleming and Annie Jump Cannon and their colleagues at the Harvard College Observatory, found its fullest expression as the horizontal axis of the Hertzsprung-Russell diagram. The sequence of spectral types, OBAFGKM, running from the hottest blue stars to the coolest red ones, became the foundation upon which our understanding of stellar populations and stellar evolution was constructed. What had begun as a practical system for cataloging the spectra of thousands of stars had become, through the insights of Hertzsprung and Russell, the backbone of modern astrophysics, a framework that continues to guide our understanding of the stars to this day. And so the work of classification, that patient sorting and ordering that occupied so many hours at the Harvard Observatory, proved to be not merely a preliminary task but an essential foundation, a gift to future generations of astronomers who would build upon it in ways that its original creators could scarcely have imagined. And so we come now to the final refinement of stellar classification, a quiet culmination of over a century of patient observation and incremental understanding, which took place in the years between 1937 and 1943 at the Yerkes Observatory in Williams Bay, Wisconsin, where a small group of astronomers worked to create what would become the universal language for describing the stars, a system so elegantly designed and so thoroughly practical that it remains in use today, nearly unchanged from its original form, guiding astronomers across the world as they study the night sky. The Yerkes Observatory itself deserves a moment of our attention, as the setting matters to the story. This grand domed building on the shores of Geneva Lake, housing what was then the largest refracting telescope in the world, a 40-inch instrument of considerable beauty and precision, and within these walls, under the directorship of Otto Struve, there existed an atmosphere of scholarly collaboration and intellectual ambition that would prove essential to the work that followed, for Struve was a man who understood the importance of fundamental cataloging work, who appreciated the value of careful spectroscopic observation, and who created the conditions under which such painstaking research could flourish without the constant pressure of producing dramatic discoveries. Otto Struve himself came from a remarkable astronomical lineage, being the great-grandson of Wilhelm Struve and the grandson of Otto Wilhelm Struve, both distinguished astronomers in their own right, and this sense of continuity with the past perhaps gave him an appreciation for the kind of foundational work that does not grab headlines but upon which all subsequent discoveries must rest, and it was Struve who encouraged the classification project and provided the resources and support necessary to see it through to completion. The three principal figures in this final chapter of classification history were William Wilson Morgan, Philip Childs Keenan, and Edith Kellman, and their collaboration would produce what is now known as the MKK system, later simplified to the MK system, a two-dimensional classification scheme that finally, formally, incorporated the insight that Antonia Maury had recognized decades earlier, that stars of the same temperature could differ profoundly in their intrinsic brightness, and that this difference was written clearly in the subtle details of their spectral lines for anyone patient enough to learn to read it. William Wilson Morgan was born in 1906 in Bethesda, Tennessee, and came to Yerkes as a graduate student in the late 1920s, where he would remain for essentially his entire career, a man of meticulous habits and extraordinary visual acuity who possessed an almost uncanny ability to perceive subtle differences in spectral line profiles, differences that other observers might overlook or dismiss as photographic artifacts, and it was Morgan who drove the classification project forward with quiet determination, spending countless hours at the comparator examining spectra with the kind of focused attention that leaves the eyes tired and the mind full of patterns. Philip Childs Keenan, born in 1908 in Bellevue, Pennsylvania, brought to the collaboration a complementary set of skills and perspectives, having trained at the University of Chicago and developed expertise in the theoretical understanding of stellar atmospheres that helped bridge the gap between the purely empirical classification work and the underlying physics that gave rise to the spectral differences they observed, and his contributions ensured that the system they developed would be not merely a catalogue of appearances but a tool that connected observation to physical reality. Edith Kellman, whose contributions have sometimes been overlooked in historical accounts, played an essential role in the preparation of the atlas itself, the actual physical production of the standard spectra that would serve as reference points for astronomers everywhere, and her careful work in the darkroom and at the measuring engine helped ensure that the published plates met the exacting standards necessary for a true standard reference, for without reproducible, high-quality prints, the entire enterprise would have been of limited practical value. The central innovation of the MKK system was the formal addition of luminosity classes, designated by Roman numerals from I through V, which allowed astronomers to specify not only a star's temperature, indicated by the familiar spectral type letters from O through M inherited from the Harvard system, but also its intrinsic luminosity, which is to say how much light the star actually produces as opposed to how bright it appears to us from our particular vantage point in space. Class 1 was assigned to the supergiants, those immense and luminous stars that shine with the light of tens of thousands of suns, their atmospheres so distended and their surface gravities so low that their spectral lines appear notably narrow and sharp, and this class was further subdivided into IA for the most luminous supergiants, IJAB for those of intermediate luminosity, and IB for the less luminous members of this exalted category. Class 2 designated the bright giants, stars of considerable luminosity but not quite reaching the extreme sizes of the supergiants, while Class 3 encompassed the ordinary giants, stars like Arcturus and Aldebaran, whose names we know from antiquity but whose true nature as expanded, evolved stars was only then becoming fully clear. Class 4 was given to the subgiants, stars in transition between the main sequence and the giant branch, their spectra showing characteristics intermediate between the two, and finally Class V designated the main sequence stars, also called dwarfs, not because they are small in any absolute sense, for our own Sun belongs to this class and is hardly tiny, but because they are smaller than the giants and supergiants that share their spectral types. This addition of luminosity class finally codified what Antonia Maury had recognized in her division of spectral lines by width, the realization that line width correlates with surface gravity and hence with stellar size, and it is worth pausing here to acknowledge this connection, this thread of continuity running from Maury's careful observations in the 1890s through to the MKK system of the 1940s, a validation of her insight that came too late for her to see it fully celebrated, though she did live until 1952 and surely knew that her work had found its proper place in the edifice of stellar astronomy. The technical challenges involved in creating the MKK system were considerable, for the entire utility of a classification system depends upon its reproducibility, the ability of different observers working with different telescopes and different spectrographs to arrive at the same classification for a given star, and this reproducibility in turn depends upon having clear, unambiguous standard spectra against which all observations can be compared. Creating such standards required first the identification of stars whose spectra were sufficiently typical of their classes to serve as defining examples, stars that did not show peculiarities or complications that might confuse observers, and then the production of high-quality photographic spectra of these standard stars at sufficient resolution and signal-to-noise ratio to reveal the diagnostic features clearly. The spectrograph at Yerkes, attached to the great 40-inch refractor, was well suited to this task, and Morgan, Keenan, and Kellman accumulated over several years a collection of spectra that represented the full range of stellar types and luminosity classes, selecting and re-observing until they had assembled the 55 standard spectra that would form the core of their atlas. The resulting publication, titled simply An Atlas of Stellar Spectra, with an outline of spectral classification, appeared in 1943, a slim volume by the standards of astronomical treatises but one of enormous practical utility, its pages containing photographic reproductions of spectra arranged to illustrate the progression of spectral types and luminosity classes, accompanied by detailed descriptions of the features that distinguished each class from its neighbors, the line ratios and profile, shapes and molecular band strengths that an observer should look for when classifying an unknown star. The timing of the publication, in the midst of the Second World War, meant that its initial distribution was limited and its impact somewhat delayed, but in the years following the war's end the MKK system spread rapidly through the astronomical community, adopted first by observatories with active spectroscopic programs and then gradually becoming the standard framework for stellar classification worldwide. The International Astronomical Union, that body which coordinates nomenclature and standards across the global astronomical community, formally adopted the MKK system as the standard classification scheme, ensuring that astronomers in every country would speak the same language when describing the stars, and this adoption transformed the system from a useful tool into an official standard, embedded in databases and catalogues and teaching curricula around the world. The notation that emerged from this standardization became the universal shorthand of stellar astronomy, compact and information-dense, so that when we write O5V we specify a main sequence star of spectral type O5, hot and blue and massive, while G2V describes our own Sun, a yellow main sequence star of modest temperature and ordinary luminosity, and M33 denotes a red giant of spectral class M3, cool and expanded and in the late stages of stellar evolution. Each such designation carries within it the accumulated knowledge of more than a century of observation and theory, encoding in just a few characters the star's surface temperature, its chemical composition within broad limits, its surface gravity, its approximate mass and radius, its evolutionary state, and its absolute luminosity, a remarkable compression of information that allows astronomers to communicate efficiently about objects whose true complexity would require pages to describe fully. Morgan himself continued to develop and refine the applications of spectroscopic classification throughout his career, and one of his most significant contributions came through his work on spectroscopic parallax, a technique that uses the luminosity class of a star to estimate its true brightness and hence, by comparison with its apparent brightness, its distance from us. This method of distance determination proved essential for mapping the structure of our own Milky Way galaxy, for the individual stars in the spiral arms are too distant for geometric parallax measurements to be practical, but their spectra can be obtained and classified, and from the classification their distances can be inferred, and it was Morgan, working with collaborators including Stuart Sharpless and Donald Osterbrock, who used this technique to demonstrate conclusively that our galaxy possesses spiral arms like those visible in external galaxies, a fundamental insight into our cosmic address. And so we see how the classification system developed for purely descriptive purposes became a tool for understanding the very structure of the universe, how the careful cataloguing of spectral differences initiated by Fraunhofer's curious dark lines led eventually to a map of the galaxy itself, a progression that neither Fraunhofer nor the Harvard astronomers could have anticipated but which grew organically from the foundation they had built. It is worth reflecting, as we near the end of this account, on the remarkable arc of understanding that connects Joseph von Fraunhofer's observations in 1814 to the publication of the MKK Atlas in 1943, a span of 129 years during which the mysterious dark lines in the solar spectrum were first counted and catalogued, then identified with specific chemical elements, then recognized as keys to stellar temperature and composition, and finally incorporated into a comprehensive classification system that revealed the physical nature of the stars themselves. Fraunhofer counted 574 lines in the solar spectrum and labeled the most prominent with letters of the alphabet, having no idea what caused them, and from this purely empirical beginning grew an entire science of stellar atmospheres, a field that today can calculate the temperature, pressure, chemical composition, magnetic field strength, rotation rate, and radial velocity of stars thousands of light-years distant, all from the analysis of those same spectral lines. The women of Harvard College Observatory, Williamina Fleming and Antonia Maury and Annie Jump Cannon and Cecilia Payne-Gaposchkin, built upon this foundation with their careful classification of hundreds of thousands of stellar spectra, creating the system of spectral types that still forms the basis of our stellar vocabulary, and though they worked under conditions of professional inequality that limited their recognition and their opportunities, their contributions proved indispensable, their insights foundational, their legacy permanent. And Morgan, Keenan, and Kellman completed the structure by adding the second dimension of luminosity class, by creating the reproducible standards that made consistent classification possible, by publishing the atlas that served as reference and training tool for generations of astronomers, and by demonstrating the power of careful spectroscopic observation to reveal not just the nature of individual stars but the structure of the galaxy they inhabit. Tonight, as you settle into the comfort of sleep, you might picture those photographic plates in the Yerkes darkroom, the spectra of standard stars fixed in silver halide crystals, each plate a small piece of encoded starlight, carefully processed and measured and compared, the patient accumulation of knowledge that allows us now to look at any star in the sky and understand, at least in broad outline, what manner of object it is, how hot and how luminous and how large, where it stands in the sequence of stellar evolution, and how it relates to all the other stars that populate our universe. The sky that seemed so mysterious to Fraunhofer, its dark lines unexplained and perhaps unexplainable, has become through the accumulated efforts of many patient observers a legible text, a cosmic manuscript whose alphabet is the spectral line and whose grammar is the physics of atoms and light. And we are all the inheritors of this tradition of careful observation and gradual understanding, this patient unfolding of nature's secrets through the application of human curiosity and human diligence across the generations.